This conference will now be recorded.
Yeah, Ranjan, good morning.
Yeah, good morning, sir.
Yeah, can you hear me?
Yeah, yeah.
Yeah, how to, I think go to meet might be the software I don't use much. So how to start the presentation?
So there is a near the camera there is a option screen. So it's coming. Your slide is coming.
Oops,
Your slide is coming.
just a minute. Let me leave the meeting, then I'll rejoin. So, PPT शेयर कैसे करना है?
Sir, the logo has screen. उसमें click कीजिए.
I'll
आपका
just check
screen
it quickly.
आ रहा है. PPT open करने से हो जाएगा.
I have PPT open with me. Yes.
Yes, it's coming. If you can make it slideshow.
Which part?
Down below. Below IIT Guwahati. The
Recording already started. Screen. Share. Now you see the screen?
no, it's not coming. There is an application. You select the application. There's a screen option, application option. Yeah, it's coming.
Okay.
You can make it slideshow.
My camera should be on, but it is not on. Reattach camera. Yeah, notice on. It is little bit different. Okay. Reattach camera. Everything is okay now, Ranjan? At your end?
Sorry, sir?
Everything is okay now?
Yeah, yeah.
But I'm still seeing several small screen of GoToMeet instead of my full screen.
It comes like that.
Uh,
Full screen is coming.
how to make the full screen here? How to minimize this part?
You have to screen.
But still some part is right there. 52 already showing. People can see your screen. So you are seeing full screen?
Yeah, it's full screen.
Okay. But some of the part of my screen is covered by this window of GoToMeeting.
Yes, sir.
So how to put it in background?
If you minimize it, there is a minimize option.
There is
Near
no
the
option of minimize. Oops. Yeah, now it is okay.
yes. Fine.
Ranjan, it is okay now.
Yeah, it's okay. Fine.
Okay.
Should we start, sir?
Yes, sure, we should.
So a very good morning to one and all. So welcome to the first session of day 4 of this ATAL Academy sponsored faculty development program on recent trends in upstream petroleum technology that is organized by the Department of Petroleum Technology, Dibrugarh. It is my privilege to welcome our esteemed resource person this morning, Professor Pankaj Tiwari sir of IIT Guwahati, who will speak on the subject of natural gas engineering. Dr. Pankaj Tiwari sir is currently working as an associate professor in the Department of Chemical Engineering, IIT Guwahati. He obtained PhD degree from the University of Utah, Salt Lake City, USA, MTech from IIT Kanpur, and DE from MIT Gwalior. His research interests include conventional and unconventional energy resources, enhancement recovery, process design and development, and kinetic studies, modeling, simulation and optimization of chemical processes, characterization of complex organic solids and their products, and conversion of biomass and waste plastics to useful chemicals and fuels. He has more than 40 international publications and conference presentations, invited talks to his credit. At IIT Guwahati, he is the faculty coordinator, Federation of Indian Petroleum Industry, FIPI chapter. Please join me in welcoming Professor Pankaj Tiwari, sir. Over to you, sir.
Yes, thank you, Dr. Ranjan. Right now, what I'm seeing is my screen only, not my video and your video. So I'm assuming everything will be okay. In case during the presentation or during the discussion, I would say anything that got disconnected or something happens, I'm keeping my mobile with me. So please give me a call. Okay. I hope nothing will happen wrong during the talk. Yes, thank you very much. You already mentioned about my degree and research area, so I can skip this slide, just mentioning few things. At IIT Guwahati, I'm also associate faculty of the Center of the Environment at IIT Guwahati, working as a member for Green Office, and we are having a special program, Food Science and Technology. It is a joint degree program with DibrU University. I'm taking some lecture and associate with this program also. So let's go, I think, straight to the, oops, it's not going up, slides. Yeah. So natural gas engineering is the subject that I don't do research in it, but I uh, taught this course at IIT Guwahati for 4 or 5 times, and then I also developed the MOOCs course. Some of you might have gone through the MOOCs course on natural gas engineering, where I have this course. So this lecture is actually the summary of that 20 hours MOOCs course. I'll try to summarize all those things in 2 hours. You might be having several questions during the course of this 2 hours lecture. I would suggest you to stop me in between instead of waiting till end and asking question. By that time, maybe going back to the slides, and you might have forgot the question also. So better if you have question, you asking at the moment you are having the questions as we are progressing. Okay, so this natural gas engineering lecture will be covering about some perspective of the natural gas, its properties, measurement, production, how to process the natural gas, and transportation. Brief idea I'll give you about the unconventional natural gas resources also, and then finally what is happening in natural gas in terms of its utilization. Okay, so with this, let me start the talk. First and foremost is the acknowledgement, because as I say, I don't do the research, but I compile the material from several books and the notes or resources. So I would like to acknowledge all of them before making the presentation. So natural gas production system, if you look on the left hand side, this is any conventional reservoir. Reservoir well that is producing any type of the fluid. That fluid could be oil, gas, and water. Generally, for the water, we don't have such kind of the complicated system as we are having water system at our home. So this represent for the petroleum reservoirs fluid, that is the gas and oil. As this lecture is focused on the natural gas only, so I'll just keep my talk near the natural gas system only. So the lectures are in the MOOCs course are divided on 20 hours spreaded starting from the introduction of natural gas till the unconventional production of natural gas. So briefly, I'll touch upon all these things during this lecture. So the petroleum fluids, if you see this left hand side diagram, we can divide this diagram into 3 parts. Okay, first one is this reservoir. That is the place where the reservoir fluid along with the water are stored. So this is one section. Second section is when this reservoir fluid is reaching to the production string or the production well at the bottom part, it is traveling all the way to several thousand-meter distance and reaching to the surface. So this is called the WPR, wellbore performance relationship. So first one, the reservoir part is the IPR, where we understand how the flow is happening towards the production well. Second is WPR, how it is traveling all the way through this production stream. And once it reaches to the surface, we are having a wellhead. Actually, this is the only visible part when you visit any field, either it is a gas or oil field. You will see the only visible part is this wellhead. Other things are underneath the surface; they are not visible. Other two parts, and this wellhead is having several accessories for the safety purpose, measurement purpose, and the controlling of the production purpose. One of the device here is called the choke. So we will understand about how this choke can control the production. After that, whatever you see, those called the surface facilities. And first of the equipment that fluid encounter once it produced to the surface after the Christmas tree, it is the separator. Separator separate the fluid into different phases based on the gravity, or the design of the separator will determine how effective separation can be achieved. After that, we are having other facilities like how to separate the natural gas. First one in the separator, then this natural gas is having some water molecules, some unwanted things, some valuable things. Those need to be separated out at the surface facilities itself before we are transporting them or sending them to the consumer. Okay. So this production well that I mentioned associated with the surface facilities for the case of conventional natural gas production. In case of oil well, most of the facilities are not required. After the separator, the oil can be transported or can go to refinery or can go to the place where it should be after the separator. The transportation we will discuss in detail. Again, a brief idea here is how much quantity we are transporting and at what distance we are transporting. The mode of the transportation will be determined based on that. A rough sketch is here that says the fluid, either it is a gas or the oil. This diagram is for the gas. Okay, where the pipeline is the most effective way if quantity is not very large and the distance is not very large, but the quantity is large. So we can lay down the pipelines. Other mode are LNG, CNG, and some other way. We will discuss later on. This is just the idea about the 2 hours lecture. So the gas that produced from the reservoir is the unrefined natural gas. While what we sell out to the customer, the natural gas is mostly the methane. Of course, some lighter fraction of the hydrocarbons are also there. Some of the non-hydrocarbon, those gases, those are not separable, will also be part of the natural gas that is reaching to the consumer end. Before we start, another disclaimer kind of the things about the reservoir engineering, or especially when you are dealing with the production part. The unit system is not very straightforward. What we learned is like SI, MKS, CGS. Those unit systems are not completely applicable for the production engineer or reservoir engineering calculation. The unit system is called the US field unit system. That is the like combination of several unit system. But these are the terminology, those are used by the reservoir engineer. For example, the area is not meter square, feet square, it is acre. Okay, length is feet, permeability is millidarcy, pressure is often measured in the PSI, and the production rate or the flow rate or STB per day for the oil, MSCF per day for the gas, not the standard like meter cube per second kind of the thing. So you have to be very careful when you are dealing with the calculation of the reservoir, especially natural gas engineering for this course. The conversion need to be applied before you are doing any calculation. So in the conventional natural production system, we are extracting the fossil energy from underneath the surface, correct? It is very deep down where we drill the wells and get the fluid produced to the surface. So this fossil energy is actually classified as three parts: gas, oil, and coal. So it is actually gas phase, liquid phase, and the solid phase. All three are the fossil energy substance. Okay. What exactly happen is shown in this diagram. We understand this theory of how this fossil energy produce. What what exactly happen is this temperature and time, they play the role in the production of, you are getting the oil, gas, and coal. Of course, the depth of the reservoir also is another parameter. Depth means as you are going down, the temperature is increasing, the pressure is also increasing. Okay, so as you are having the longer time on this scale, you will see even the lower temperature can convert this kind of the substance into oil, gas, and coal. But this process happened over the geological time scale. So what you seeing in this picture is above the surface, and similar kind of the arrangement is underneath the surface. The major difference is above the surface, this is not converted into oil, gas, and coal. This is mainly a substance or a system where you are having the mineral matters associated with the organic matter. That organic matter is called the corrosion. That corrosion gets converted into bitumen or directly to oil, gas, and coal. If you are leaving the system at a higher temperature and higher pressure for a longer time, first it will convert to solid phase, then it is going to convert into oil, and then finally it is going to get converted into gas. So the general thumb rule is that as you are going deeper underneath the surface to find out where the petroleum fluids are there, the places are having the oil and gas. But if you are going much deeper and much deeper, the chances of getting the gas reservoir or gas fluid is more compared to the oil, because under, as you are going down, the pressure and temperature is more, and the chances the fossil fuels is converted into natural gas. So the organic material on geological time scale, geological time scale means not a lifespan of one person. It is like several thousand years over that time, or it's called geological time scale. Over that time, the organic matter got converted into this fossil energy, one of them. So let's come back to the natural gas part. You see on the right hand side, you are having this diagram where a well is drilled to a place where the fluid are stored. You can see the water, oil, and gas. Okay. To get this fluid stored in a particular location, you need three types of the arrangement. One is the source rock, from which these fluids are converted from the organic matter into oil and gas. Second is the reservoir rock, where these fluids are stored. It should be a porous and permeable region. And then the cap rock. Cap rock, because of that, these fluids are stored at that place. Okay, they are not coming out to the surface. It is impermeable rock. If it is not impermeable, it is having some permeability, then the fluid will travel because of the pressure gradient, and you will get the oil and gas at the surface without reaching to that point. But because of this cap rock, we need to drill the well to a place where these fluids are stored. Okay, how to know where to drill? There is a well established technique now. Geologists and geophysicists, they survey the area, they find out based on their several techniques like geological survey, seismic survey, they find out the potential place where the drilling should be performed. So, and we are having the good chances of getting the fluid there. Now advanced techniques are there, computer model are there, so the success rate is good. Long time back, like 30-40 years back, the success rate was very low. You are drilling 10 wells and you are getting only one well is a success, other are the dry well. And a lot of money is involved in drilling the well, so the precise prediction of the place to drill the well is very much important. So not going detail of, I think other lecture already covered about how the seismic survey and geology and geophysics do work. Let us come back to our petroleum reservoirs classification. So once the well location is identified, we started drilling the well, well completion is done, the production team come forward and they started taking over the production part. Now the first important point comes out, what type of the well it is. It is a gas well or it is the oil well. Okay, there is a further classification in those, but broadly it is a gas well or the oil well. So the GOR is one of the parameter that can tell us what type of the oil well, what type of the reservoir well it is. So once the fluid produced, it is passed through the separator. You are getting a good separation in the of the gas and oil and water. You calculate the ratio of the gas production to the oil production, you will get the GOR value, and that GOR value can tell us the classification of this particular well. In the oil sector, there is other parameter that can also tell us the sub-classification of the oil reservoir based on the degree API and the color. So the experienced person, they use GOR, degree API and color to classify their reservoir. In case of gas reservoir, you can have the dry gas well, wet gas and condensate well. Okay, depending again on the GOR value and other parameter like the amount of the water present or not, but the classification is mostly based on the GOR. We will discuss in the next slide. So once the well is identified as a gas reservoir well, we also need to understand its thermodynamic nature. And this diagram shows pressure temperature relationship for the natural gas, how the natural gas will behave, or the fluid that is getting produced from the reservoir they will behave under different temperature and pressure condition. Understanding of the thermodynamic nature is very much important, because see here at the reservoir part, at the bottom section, we are having the different temperature pressure. Now this string, the valve bore string, is also very large, that is several thousand meter long. This also having a different temperature and pressure. And in the next slide, I'll mention about the natural gas is actually not an ideal gas. It is the real gas. It is having the compressible nature. Because of that, its properties, its behavior changes as the temperature and pressure is changing. So the thermodynamic nature is very much important to understand. We are going to get how much percent. Yeah, please. Yeah, any question? Okay, I'm assuming I'm going further. So the GOR that I mentioned is the gas oil ratio. If it is greater than 1 lakh SCF per STV, it is a gas well. If it is less than 5,000, mostly you are getting the oil, just a small amount of the gas is also produced. It is a oil well, and in between it is a condensate well. Condensate well is where you are getting the gas with high content of the liquid hydrocarbon pH. Okay, the gas well further classified is associated or dissolved gas or non-associated gas, where the non-associated gas, the reservoir with minimum oil, it is mostly the gas is getting produced. On the thermodynamic part, on the phase diagram, as I mentioned, everything is happen under the two-phase envelope, where the bubble point is on the one side, dew point is on the bottom side, and depending on the temperature and pressure you are having, the fluid can be classified. It is a region where you are getting the black oil. Depending on the reservoir temperature and pressure condition, you might have a black oil, volatile oil. But on the gas side, if your temperature is in this region, high temperature region, you are mostly having the dry gas. But when your temperature and pressure is falling within this envelope, two-phase envelope, you are going to get the wet gas, or the wet gas composition will vary depending on the tie lines within this system. So this is not a simple, just one simple envelope. The shape of the envelope will depend on the composition. Okay, what are the composition of the gas phase you are producing, and accordingly the nature of this curve will also be different. So the critical point or the other parameter will be shifted accordingly as per the composition of the gas, and depending on where your separator is, you are going to get what temperature and pressure you set up your separator. So for example, in this wet gas, your separator is somewhere here, the temperature and pressure condition at the separator, and because of the composition of the gases, the production happening that is also having within this envelope, it means some percent of the liquid will also get produced. While in case of the dry gas well, your separator condition are somewhere outside this envelope, and mostly you are getting only the gases. So with this background, what natural gas is, it is a complex mixture of hydrocarbon with a minor amount of the inorganic compound. What those compounds are, it ranges from C1 to C7, or sometimes C8, and other compound can also be there, but mostly C1 to C6 or C7. Non-hydrocarbon gases could be carbon dioxide, H2O, sulfur dioxide. They are in a small percent, but they present there. They are present in the natural gas. And because of the presence of these inorganic gases and the variation in the hydrocarbon gases, lots of the properties of the gas or natural gas vary. So what happens? Let's take example when we want to find out the properties of the methane. We can go to any standard thermodynamics book. We can find out all properties of the methane because it is a pure substance. But when we talk about the natural gas, it is a mixture and the composition also changes. You are supposed to calculate those properties based on the correlation already established or the graph there or some mathematical procedure. This natural gas, because the compositions varies, its ignition or the flame value also vary, like when it will be ignited. So the air gas mixture, when it is in the range of 5 to 15%, then we get the natural gas burned out. Otherwise, the fire will not catch up, or the fire will get extinguished if the air ratio is increasing. If we burning just the methane, combusting the methane, it can give us the energy up to 891 kilojoule. It gives exactly 891 kilojoule, 1 mole of the methane. But as I said, the natural gas is a mixture. So the value of the energy produced varies from 500 to 1550 BTU. On average, it is 1031 value. Because the value may be lesser than the methane. As you go on higher hydrocarbons, the energy content should go up. But because of the presence of these non-energy releasing content or inorganic component, the energy may go down up to 500 BTU also. It is a colorless, odorless, combustible in nature, and because of all this, it is considered the clean fuel compared to the oil and coal. Several classifications are there. The percentage of these compounds vary, like mostly dominated by the methane, 70 to 90%, but other compounds are also present. The classification could be based on the composition. So lean gas, rich gas. If the gas is having mostly the methane, it is a lean gas. If other hydrocarbons have higher carbon number like C2, C3 are present, it is a rich gas. Sweet gas, when the sulfur compounds are present, when we remove them, it's a sweet gas. And some other classifications are also there, not going in detail. Important one is this gasoline. So gasoline is not the gas, it is a petrol. Okay. And in USA, it's called the gas. That's also different. When you go to any gas station, you are not going to get the gas, you are going to get the petrol. Okay, or gasoline, I would say. Domestic gas, that is also not the natural gas. Our domestic gas is the propane and butane, higher hydrocarbons, C3 and C4. They are having more energy, they are more valuable, they are separated from the natural gas, bottled and supplied to meet our domestic gas need. Other terminology like LPG, CNG, GTL, gas to liquid, are also some of the form of the natural gas. So the properties of the natural gas estimation is very much required to develop the field, design the equipment to handle the natural gas, and of course the cost estimation when you are selling out your natural gas. Okay. So the properties could be density, viscosity. I'll just go through a little bit faster. Evaluation of gas reservoir and gas well, they need these properties. Production, prediction, and evaluation of the gas well, where also we need these properties. Separation process. So everywhere where we are dealing the material, any material, we need to understand what that material is, and for that purpose, we need to understand its properties. So let's say properties of the pure component are known that I mentioned. So when you are getting the natural gas sample from the field, first thing you can do the gas chromatography to find out what are the compositions are there and what are their percent. They may vary from C1 to C7, as I mentioned, some inorganic compound. So we can go to literature, find out their standard value like the molecular weight, critical temperature, critical pressure, and GC will give us the mole fraction of those compound present in it. Some may be absent or the composition may vary. I just put one of the example here. After that, as I said, the properties need to be estimated and we have to go to basic understanding or the correlation already established in the literature. The major difference with the pure gas and the natural gas is the real gas, and the ideal gas law is not going to be applicable. PV is equal to nRT is not going to work. We have to start with PV is equal to ZnRT, and that's where entire complexity of natural gas production, processing, handling bring up in the handling of natural gas. Otherwise, the basic principles of equipment design, uh, getting the balance equations almost are same. But this non-ideal behavior of the natural gas that makes the system very, very complex. So if we go to the literature, let's say compressibility factor of the natural gas, that Z I was mentioning. If you go to the literature, you will say such kind of the complex diagram were produced long time back. And these diagram are in the form of pseudo reduced pressure and pseudo reduced temperature. Pseudo reduced pressure on this scale and the inclined lines within this graph are pseudo reduced temperature. So first you need to know the gas composition, then pseudo reduced temperature, pseudo reduced pressure, then you need to read this complex chart, then only you will get the compressibility factor value. Later on, this is very old, like I mentioned 1942. Later on, these diagrams were converted into some mathematical expression. Not only the organic component, inorganic component are also present, their percent will also influence the parameter estimation. So those diagrams, these kind of the complex diagram, they are used for the correction factor for the inorganic component present in the gas. Later on, those are converted into mathematical equations. This is for the viscosity estimation, and we are having some good correlation. Those can read those are based on reading this chart. We can use for calculation purpose, for writing the mathematical model in the computer. So let's start with the basic property, specific gravity of the gas. This is gamma g. It is simple molecular weight of apparent molecular weight of the gas divided by the molecular weight of air. How to know the apparent molecular weight? We know the composition of the gas. We know individual molecular weight. Apply the chain rule, you will get the apparent molecular weight of the natural gas mixture. Pseudo critical temperature of the gas. It is pseudo because it is about the mixture. Again, apply the chain rule with respect to individual compound. Similar you can do for the critical temperature. Once you know critical temperature, critical pressure, based on this chain rule, but these chain rules are not accurate one. If you want a more accuracy in your data calculation, then you can go to some correlation develop. Those are based on like gamma g, gas specific gravity. Those are also developed with the correction for the inorganic compound present in the natural gas. So these are based on those complex chart I had shown you. Several researchers have developed several things, and depending on the composition of the gas, some correlation are valid for a particular gas composition, some are not. So you have to choose a specific correlation based on what are the composition of your natural gas are. Once critical temperature, pressure are known, we can calculate the reduced pressure and reduced temperature. Remember those diagram were on reduced temperature and reduced pressure term. Now we know how to calculate them. The viscosity, there are correlation like CKB and Brill and Beck's method. CKB for the viscosity measurement. It is also very complex thing. Just simply the expression I had written is just for kinetic viscosity and dynamic viscosity relationship. Otherwise, using the method given in the diagram is very complex. Like you see here this chart, how to know the viscosity of the natural gas. The first chart is given only to measure the viscosity of the natural gas at 1 atmosphere. But we know viscosity is a function of pressure also. We have to correct for the elevated pressure because we are dealing the gas at a different pressure also. Then you have to read second chart, correct? So these correlations are there. Several scientists did it, but one of the method is CKB that can give us the viscosity. For gas compressibility, Brill and Beck's methods are there, HY methods are there. They how to understand the complexity involved in the process. You can use these methods to get the gas compressibility. Gas density is simple one, mass divided by the volume. But see here, when we say mass divided by the volume, now volume you will replace with the real gas law, not the ideal gas law, and then the compressibility factor Z will come here. To get this, you have to go to Brill and Beck's and HY method to find out how to estimate the gas compressibility factor. Some other terminology, formation volume factor and gas expansion factor, they relate one condition of to the other condition. So the natural gas is passing through different temperature pressure zone. So how the volume can be converted from one condition to the other condition, these kind of the terminology can be used. Gas compressibility, it is very important because our natural gas is compressible in the nature. You have to use the definition of the compressibility. This is isothermal compressibility. Change in volume with respect to pressure at a constant temperature divided by the original volume will give you the compressibility. And ideal gas law, it is just 1 by P, 1 by pressure, but for the real gas law, it is in the form of this compressibility factor. Some of the terminology I'm just showing you. MP, another parameter. This is just one parameter that's relate pressure, viscosity, and compressibility all together. It is a lumped parameter. Instead of estimating individual mu and Z, you can estimate the MP, because in several calculation you will see mu and Z comes together. So you can replace that using the MP. That's called the real gas pseudo pressure. Okay, so the Reynolds number also, if you see Reynolds number for natural gas, it is not rho Vd by mu, because once you replace again all those things, you are going to get this expression. So the Reynolds number for natural gas, after putting the value for standard temperature pressure, it is 20.09 gamma G Q by T mu average. Now again, you have to remember the unit, in which unit the terms are defined, otherwise the numerical coefficient will be different. Along with the natural gas, you also need to understand the properties of the rock. Rock is a substance through which where the natural gas is stored underneath the surface, and from where you are producing it. Several ways are there to understand those things, but petrophysicists, they do the rock studies and estimate these kind of the properties. Theoretical and laboratory analysis can be performed to get the physical properties. These properties vary. Porosity, these properties are porosity, permeability, fluid saturation, and some other. Okay, porosity is simple one, like oops, I don't have slide for that. So porosity is the wide volume where the fluid can store in the rock. The permeability is ability to move from one pore to another pore. This is like a flow characteristic of the reservoir formation through which the fluid will be traveling. Fluid saturation, like the volume occupied by the fluid in the reservoir domain in the porous region. If multi-phase fluids are present, each fluid will be having its own saturation as per their properties. Altogether, what I want to say, along with the gas properties, you also need to understand the rock properties. That will give you a lot of understanding about the mathematical relationship developed to deal with the natural gas. Or when you are dealing with the natural gas, you will be having a better control over the production. The Darcy law, that is the most acceptable law for understanding the production through the porous media, but it assumes certain things, like the flow should be laminar, steady state flow, incompressible fluid should be there, and homogeneous formation. And in reality, none of the condition exists in the natural gas production. Okay, our flow is not laminar. I'll show you later on. Steady state flow is a hypothetical situation. Nothing happen under steady state flow. Most of the production, either it is a gas well or oil well, it is under the pseudo steady state condition. Incompressible fluid, our natural gas is not incompressible. Actually, there is no fluid that is incompressible in the nature. Every fluid is having some compressibility, but our natural gas is definitely not incompressible. It is compressible in the nature. And homogeneous formation, our reservoir is not a homogeneous, it is a heterogeneous formation. But still we use the Darcy law in most of the calculation, and as and when required, we apply the correction factor or modify the conditions to go as close as we can go to the reality. So the Darcy law for the linear flow, if the flow is happening in the linear, this is a relationship between the flow rate and the pressure drop across the length L. You can establish the relationship, and the proportionality constant K is actually the permeability. This is the characteristic of the rock, how it is allowing the fluid to travel through. So this permeability, this is a property of the porous media that measures the capacity and ability of the formation to transmit the fluid. Already mentioned these two expressions. You can convert flow rate into velocity or velocity into flow rate. That Q is equal to area into velocity. The determination of permeability of a formation depend on several factors. That I said, our reservoir is very heterogeneous in nature, but still we can measure the permeability of a formation in the laboratory. Permeability is classified in absolute permeability when only one single phase fluid is present, but in most of the time we are having the multi-phase present. Oil and gas and water are present there. Effective permeability is used, and sometimes it is a relative permeability, that is the ratio of effective permeability to absolute permeability, that is utilized for the purpose of understanding flow of the fluid in a multi-phase system. The permeability varies in horizontal and vertical direction. There is not a constant value. It is a very heterogeneous system. So the average value can be calculated, and that average can be taken as several sample can be taken from a different location, calculating the arithmetic average, geometrical average, harmonic average, or sometimes weighing with some factor. So the sample is taken with certain height, n number of sample are taken with different height, measure the permeability of each sample, and use such kind of the relationship to calculate the average permeability. Rock compressibility, like the fluid also, as I mentioned for the gas, the definition remains same. Change in volume with respect to pressure at constant temperature divided by the original volume. But our rock is also having some compressibility. We don't observe it so precisely, but as we deal with the high pressure, the compressibility becomes important. And as we go underneath the surface, as a thumb rule, 0.5 psi per feet, the pressure is increased. And under that pressure, the compressibility becomes important. So as and when we are doing the calculation, we should also worry about the rock compressibility nature to have the precise or more accurate expressions. Reservoir diluviality is a part. I think I missed it. Yeah, enough time. So reservoir diluviality is a first place where we will start developing the inflow performance relationship. It's called the IPR. It is a place where we understand how the fluid is traveling from this heterogeneous region that is having a varying porosity and permeability. In picture, it is looking very nice, a rectangle kind of the things, but it is not. It is just to show you how the fluid is traveling from reservoir pressure to PWF, this bottom hole pressure, and the production happening through this porous media can be established. And the purpose of IPR relationship is to establish the relationship between the flow rate and the pressure drop. So this relationship depend on some important parameters: types of fluid in the reservoir, what type of the fluid you are having, flow regimes, flow geometry, number of flowing fluid in the reservoir. Let's go in more detail about that. Like types of the fluid could be slightly incompressible, compressible, incompressible. Our natural gas is compressible. Flow region could be steady state, unsteady state, pseudo steady state. I would tell you, pseudo steady state is the case where most of the time the well is producing. Steady state is a hypothetical situation. Unsteady state or transient happen when you disturb the well, or when you are starting the well or shutting down the well. Geometry could be the flow might be happening in a radial flow, linear flow, spherical, hemispherical. Situation could be many. We will focus on radial flow only. Fluid could be single phase, two phase, three phase. Let's assume we are talking about natural gas. Only single phase fluid is present. So what is compressible fluid? The properties, density or volume is changing with pressure. That happens with the natural gas. That's why natural gas is the compressible fluid. Pseudo steady state flow, where the flow is like this. Second point here, where at a particular position the flow is constant with respect to time. The change in pressure with respect to time is constant. While steady state, when the pressure is not changing at all, when there is pressure is not changing, it is hypothetical situation, because of the pressure drop, the flow is happening, and if there is no pressure drop, the flow will not happen. Unsteady state, where the pressure is changing with respect to time as well as with respect to position non-linearly. This happens at the starting of the well or end of means shutting down the tank. Otherwise, most of the time the flow is happening under semi-steady state case. This I was mentioning about the radial flow. Flow is happening from all directions. We drill the well, bottom section of the well is perforated, created the holes, and now if we created the path, because of the pressure drop, the fluid will travel towards the production string, through which the fluid will travel through the well bore. Now this arrangement of the production string could be where we are having these holes all everywhere. This is called the radial flow. We may have the arrangement, the flow is happening only linearly from the one side. This is called the linear flow. Situation could be like this, where the perforated region is lesser than the page on thickness, and you get the flow is happening in this pattern, or the flow is happening from the bottom section of the production string. There is no perforation, so this is called the hemispherical, the last one, and this is called the spherical. We create the spherical kind of the shape. This is okay. So the IPR can be established, the relationship between the pressure drop and flow rate, analytically or empirically. I'll go a little bit fast because I have more slides. So if you want to ask question, please ask there. Any questions so far? Ranjan? Ranjan, are you there? Any participant?
No question, sir. Everything is clear.
Okay, so am I audible? Yeah, please say something in between. I would be knowing I'm connected. Okay. Otherwise, online class, sometimes you got disconnected, you don't know, you just keep speaking. So I'll ask this kind of thing. Okay.
Yeah, I can
So
understand.
the IPR is also about balancing the system, that is the material balance. We will start with simple material balance. All chemical engineers know about the material balance. So what we do, we set up the material balance under certain conditions. Those 4 conditions that I said: fluid single phase, geometry radial, types of the fluid compressible, that is natural gas, and let's say flow behavior is steady state, that is simplest case, and most of the time is the pseudo steady state. We can set up the mathematical material balance for this kind of thing. Some parameters are there: skin effect, non-Darcy effect. Those I mentioned, Darcy law is under certain condition. When condition violated, we have to apply the non-Darcy coefficient also in the expression. Once we establish this relationship, some parameters come out. Those mostly the petroleum engineer talk in that comes. What is the productivity index of a particular well? Absolute open flow condition means what maximum flow rate can be achieved from a particular well. Okay, empirical methods will also be discussed. They are back pressure approach and force majeure approach. So let's say what is that material balance? So the flow regime I already mentioned. This is the case when the flow rate is not changing with time. This is with changing initially with time. The transient happen and remaining time it is a pseudo steady state case. Okay. So when I said the balance we have to do, so the material balance is called the continuity equation. Now flow is happening, we have to include the transportation equation. We are flowing the compressible fluid, we have to include the compressibility equation for the natural gas. And once we do this balance, shell balance, we get the OD or PD developed that need to be solved. For that we need the initial and boundary conditions. Okay. So material balance is simple. What goes in is equal to what comes out plus what left is accumulated within the system. There is no reaction happening, non-reactive system. So we just need to worry about the reactive part. So basic form of IPR, let's start Darcy law for the transport equation. Compressibility, we can use the compressibility definition, and equation of the state of the real gas law can be used for the handling compressibility part. The expression that you got by the analytical looks like this. You remember this MP I said this is a combination of Py mu Z. Okay, it is a lumped parameter. So the Q versus pressure drop, this is a pressure drop relationship can be established. This is the expression for pseudo steady state case, where the permeability of the formation, page on thickness, are part of this expression. R is the reservoir radius, RW is the valve radius, S is the skin effect. Skin effect means when you are producing over the time some solid particles, some grease part or something, by any mean there is additional pressure drop near the valve bore because of some deposition. Okay, that's need to be counted because that's create additional pressure drop. And dq is the non-Darcy coefficient. D is the non-Darcy coefficient that's need to be included because the Darcy conditions are violated. When it is violated, when the flow is happening from all direction, the velocity is increasing. Why the velocity is increasing? Because area is getting reduced. From larger area it is coming to a smaller area, and that's where the laminar conditions are not existing near the valve region. For that purpose, you need to include the non-Darcy coefficient in it. That I said, the assumptions are there. Still in developing this thing, we made certain assumptions. We still saying it is a compressible fluid. Homogeneous reservoir is assumed. Isotropic reservoir means the properties are not changing with respect to direction. Still, we are not having the complete expression. You can modify it with some more complexity. But this is one of the simplest pseudo steady state analytical expression. How to get this? I'll go a little bit quick. Mass balance in is equal to out, in the shell balance is equal to accumulation. Apply the same principle. The thickness is low, you will get the PDE. Now Darcy law can be applied in it for the flow and the compressibility of the fluid. You can convert this volume into density form.
एक बड़ी
Sorry.
बात ये इस हार में देखना चाहिए और सबको खुश होना चाहिए कि राजनीतिक दलों का अगर आप
Hello. Hello.
Yes, sir.
Yeah, I got Prime Minister voice. Is it from my side or you somebody else?
It is from the other side. It's not from here.
Okay. Okay. Good. Please mute. Okay, so the compressibility of the nature, so you can include all those equations and you get the mass balance equation. This mass balance equation is complex. It is having no analytical solution. For that, you have to go with the approximation, and the approximation could be where you are assuming Py mu z is constant. P square approach, you can convert it into P square form. I'm not going detail, or you can convert it into MP form by making this lumped parameter. Now, three expressions are there. Which one should be used? So if you are in this pressure range, 2000 below 2000, use the P square approach because this is having the linear assumption. When you are above the 3000 psi, you can use the pressure approximation method, and if you are in between, use the MP approach because it is using no approximation. It is an integral based approach. It is more accurate approach. If you want to choose any one of them, go with the MP approach. Okay. So understand, if you solve this equation with the boundary condition, you will get this expression for the steady state case, pseudo steady state case. And these are in the form of P. You can do similar for the P score and MP approach. Once you establish this expression, you are ready to understand the flow versus pressure relationship. So whatever the pressure at the bottom hole, accordingly, the flow rate will be can be estimated. Okay. Still, I'm getting some voice. So somebody trying to speak, or it is just he is not, he or she is not muted. Okay. So the empirical methods are also based on this analytical expression only. If you see little bit, arrange this equation in a manner, you will get AQ plus BQ square. Whatever is in the multiplication of Q, that is the A, and this Q will multiply with this Q, you will get Q square. Whatever is in the multiplication effect, this is B. So now you got this quadratic equation. Now what is the advantage of this equation? Now you are having the well running with you, correct? Now you do the well testing at 2 points. Once you do the well testing at 2 points, you are getting the two set of the equation at what flow rate is there and what is the PWF. You change the flow rate, you will get PWF change. Now two set of the data from the well will give you the value of two unknown in this equation, A and B. Once you know A and B, you got your IPR. Now in future, whenever PWF is changing, you will say what is going to be the production. You got your own IPR equation. Okay, so this is how E and B can be estimated. Okay, so just two data set, you can solve this quadratic equation and you can get by intercept and slope. If you adjust this equation, you can get A and B and that IPR equation. What about back pressure equation? In this equation, everything in the multiplication of the pressure drop down is the C, and the non-Darcy effect of this Q power is adjusted by N. And if you take the logarithm of this, you are going to get a linear relationship. Again, slope and intercept of this part will give you the value of N and C. Once you know C and N, you know your value. Ultimate purpose of doing the IPR relationship is knowing how Q is related to the pressure drawdown. Pressure drawdown means pressure difference between the reservoir pressure and bottom hole pressure. Okay, and once you know that, you can predict in future how the bottom hole pressure change will affect the production rate, or the production rate will affect the bottom hole pressure. You can do different approaches will give you a different value. That's why the analytical expression are not that accurate compared to the empirical, because empirical are based on the field data. They are going to give you the better prediction. This is summary of the same thing. I'm just skipping it as time is there. Now over the time, the pressure will change. And you remember in the IPR equation, you are having viscosity, that is a function of pressure. So every time when over significant pressure or reservoir pressure got changed, you have to correct your data, otherwise the prediction will be different. So if 2000 pressure was there, the prediction shows like this kind of the nature. But over the time when the reservoir pressure got changed, you are going to get the prediction differently. For that purpose, you need to make some correction in the parameter A and B instead of performing the same analysis again. Should we take a break or it is okay? Ranjan, what is the plan? Continuous 2 hour? Ranjan? Yeah, any participant?
I am talking on behalf
Hello?
of Ranjan. Hello, sir.
Hello?
Hello, sir. I'm
Yeah,
talking on behalf of Ranjan, sir. We can
okay.
continue or we can take a break if you want, sir.
No, I don't want, like, if it is not a plan, I would like to continue, because I think I would need more than 1 hour, around 1 hour to.
Yes,
Okay,
sir. Then we are.
let me continue it. So once our well is ready for the production, we did not discuss the WPR, CPR. I'll discuss after this. Let's say our IPR is so useful equation. If we are having the IPR with us, we can test the well. Well testing is important, because if you want to know the reservoir pressure, you want to know the flow potential of the gas reservoir, all those things can be done by doing the well testing. Anything?
Excuse me, sir. I would like to announce something. There are some background noises coming. I would
The
like to
background noise not from my side, I think. Is it from my side?
sir, not from your side. I would like to request other people to please mute.
So one of the participant mic is on. Pranav,
Can
please
you,
request him to mute it.
Ranjan, can you forcefully mute him?
Yes, sir.
Hello, Pranav.
Participant mic is open. Hello.
Yeah, Ranjan, ask please.
Yes, sir. Now it's
Yes, sir.
okay.
Yeah.
Yes, should I continue now?
Yes, sir.
Is it okay,
Okay.
Pranab? Yeah.
Yes, yes.
Maybe some noise is there, but let us start. Okay. So gas well testing is a useful tool that used to analyze the performance and forecast the productivity of a gas well. Gas well testing is required to understand what maximum production we can get and lot of the things, because there is some regulation by the regulatory bodies what maximum production you can have. It does not mean you just got a gas well produced today and just finish off and then done, because you should have a business also, correct? So the regulatory bodies are also having certain restrictions on the production rate or withdrawal rate. You want to estimate some of the like how much gas reserve is there, what maximum production rate can be achieved, and for designing and designing the facilities and processing plant, you need to do the gas well testing. So gas well testing is done in two ways: pressure transient test and diluvibility test. Pressure transient test means you're doing something with the pressure. Diluvibility test is you are using the IPR that I just shown you. Okay, diluvibility test means establishing the relationship between the pressure drawdown and the flow rate. It means you are understanding how the production will be as the pressure difference is changing. So let's go further. Okay, so this is the IPR that we developed, but we did not discuss about this transient part. Okay, transient part equation here in this reservoir. Let me start from here. So you are having a well through which the production is happening Q at a constant flow rate. When you start at time t is equal to 0, the pressure at the bottom hole is equal to the reservoir pressure. When you start it, suddenly the pressure drop happens. It is a transient time when the pressure is changing with time. Over the time, it will change. Then after some time, it will be changing linearly. That is the pseudo steady state or semi-steady state condition. Now the equation in the early time when the transient time dependent part is there, for that purpose equation is little complex that we did not discuss. Important point here is it is function of time. You can see here function of time. So the pressure change is a function of time. How much time is required to reach the pseudo steady state, that can be calculated, and that is a function of porosity, permeability, radius of the reservoir, viscosity of the gas, and so on. For the pseudo steady state, we already seen this equation. Same equation is here, correct? We discussed previously. Now, if I'm having a well, I'm producing under this condition, I have to use transient equation. If I'm using under this condition, I have to use the bottom equation. Clear? When I'm performing the test on the well, which equation I should be using? When the pressure is changing with time, use this first equation. When it is not changing with time, use the second equation. So the pressure transient method of gas well testing use first equation, diluvibility test use the second equation. You remember these equations? Under the pseudo steady state case, this is the force mayor equation, correct? If non-Darcy coefficient is not required, this Q square will not be there. Everything is clubbed with A only. This is a simple equation, linear simple equation. If non-Darcy conditions are also existing there, you are having this quadratic relationship, or better to always go with a quadratic relationship, because if it is not there, the B value will be very, very low compared to A. This term will be having not much effect on the mathematical expression. So this is a second order equation. What about when it is a time dependent? Similar way, we can arrange that equation. Anything related to log T will be having the M as a multiplication factor. Remaining part will be A. And in the other quadratic form, A is a time dependent with respect to Q, while B is constant with respect to Q square. So for the transient part, we can set up that equation. See here, this equation, which I was saying here. So the first equation can be arranged in AQ plus BQ square. Second equation can also be arranged in AQ plus BQ square. Difference will come here is a function of time. Okay, that need to be taken care, while in the first case it is not. Okay, so what is pressure transient? You create the disturbance in the reservoir. pressure disturbance. So when you start production, suddenly what you do, the reservoir pressure and bottom hole pressure was same. Suddenly you start producing, the pressure difference should be there, then only the production will happen, and suddenly the pressure drop will be under the transient time. And under that conditions, you are monitoring how the pressure is changing with respect to time and using this equation to get the relationship. While in reliability test, you just measure under the pseudo steady state, some information there. So the pressure transient test can be drawdown test, build-up test, pressure falloff test, injectivity test, or it can be done in a single well or in multiple well. In multiple well, you are having one well as you are creating the disturbance while you are monitoring or observing the effect of the disturbance in the another well. While in the single well, you measure, you create the disturbance in the same well and you measure in the same well. A reliability test are conventional, isochronal, and modified isochronal. We'll discuss a little bit. Drawdown test that I said, your well was under this certain period. Okay, drawdown means you are dropping the pressure. So simple. Okay, so you are having a well, you shut down it for a significant time. There is pressure established underneath the surface. The underneath the surface means reservoir, and your bottom hole pressure is the reservoir pressure. Be careful here. Okay, and now suddenly you open the well. When you open the well for the production at a constant flow rate Q, okay, what will happen? The pressure will drop. Now with respect to time, you can monitor 3-4 places the pressure, and you can use that AT plus BQ score, AQ plus BQ score relationship, and you will be able to get the constant there. Okay, now this kind of the information is very much important. If you know, for example, you already knowing some of the parameters are unknown to you. You establish that relationship and you can find out. You can find out the average reservoir permeability, is skin effect is affecting or not, is there any damage in the reservoir well production stream, pore volume, reservoir is inhomogeneity presence in the reservoir. So a lot of the information can be obtained when you perform pressure disturbance test. Similar to that test, there is pressure build-up test. In this test, you build up the pressure. How you do it? Your well was producing at a constant flow rate Q. Here, everything was okay, nice. At time T is equal to 0, suddenly you put it in the non-production condition. You just shut down it. What will happen? You were having some bottom hole pressure here. Suddenly, the bottom hole pressure will increase. It will try to attain the reservoir pressure. Okay, so the pressure will build up. Again, you are having the relationship between the time and pressure that you can use for this purpose. In reliability test, you use either back pressure equation or force mayor equation. Back pressure is easier. You just have to log and C and N can be calculated, or any of the equation you can use. What you need to do, you have to run the well for few cases to get the value of C and N. Okay. Now, how to get this IPR relation for a well? You will see we can perform this conventional back pressure test, that is flow after flow. Isochronal, as the name justified, is some constant pressure condition. Modified isochronal means you are doing something with the pressure. Let's see what happens. Conventional back pressure test, you started producing from a well and you know how much time is required to stabilize, because you know this TPSS. So you were producing at a constant flow rate Q1. Initially you were having not a production, you started just a constant production Q1. What will happen? Here the pressure drawdown will happen as you start producing, and the pressure will stabilize PWF on bottom hole pressure. Now you increase another flow rate, further flow rate Q2. What will happen? Further pressure drawdown will happen. Depending on the flow rate, the pressure will drop. Every time you are changing the flow rate, the pressure is dropping further. Okay, and then you shut down the well. When you shut down the well, the pressure will come back to the reservoir pressure. Not necessary or always increasing the flow rate. You can do another way. Constant flow rate, drop, then drop and drop. the reverse trend will be obtained. Okay, so the normal sequence is often done, but reverse sequence can also be adopted. Now what we got in this? What we got the relationship between the Q, this constant Q1, and PWF1. So if I am flowing at this Q1, the PWF1 will be this much. If I am flowing with Q2, PWF will be PWF2. So I got 3-4 point. I can use those 3-4 point to get the relationship between the pressure and the flow rate. You remember this, I said you can use the MP, P square or P approach depending on you. So you are using P square approach. In this you plot P square versus the flow rate and you are going to get the linear relationship. This curve called the stabilized deliverability curve, because the flow is getting stabilized after some time, then only you are increasing the next flow rate. Slope will give you 1 by n, and you will be having a condition, the zero pressure. Let's say this is the pressure where the pressure difference is 0. Okay, I mean to say pressure difference is maximum. Zero pressure means this PWF is 0. You open the well, there is no pressure at the bottom hole. The maximum flow rate you will get, correct? Because the minus part is taken out, the maximum flow rate you will get, that's called the AOF, absolute open flow condition. Okay, and after doing this run, you got your IPR. Now you are having your own equation. You can predict the well performance. Okay, once the well has been tested, IPR is constructed, future performance and the properties can be estimated. What happened in isochronal testing? In isochronal testing, you don't wait the reservoir to reach the pseudo steady state condition. Very simple one. You do in a little bit different way. So you were having the production Q1, suddenly from 0 you started production Q1, you let it happen. Instead of in the conventional back pressure, you are increasing the flow rate. Here you shut down the well. So here it is a pressure drawdown. Here what will happen? When you shut down, pressure will come back to the reservoir pressure, correct? And you wait till the pressure is reaching to the reservoir pressure. And then you again change the flow rate, pressure will drop will happen, shut down the well, pressure will come back to the reservoir pressure. So this is the way you do your 3-4 runs, and at the end you do the extended flow rate, because this extended flow rate is actual condition where the pressure is going to be step, correct? It will try to reach the pseudo steady state condition. Now the advantage of this compared to the previous one, here you don't need to wait for TPSS time, that is the time to reach the pseudo steady state condition. You just come back to the average reservoir pressure and change the flow rate. Okay, and you got the relationship again, Q1 versus PWF1, Q2 versus PWF2. But remember, these are not the stabilized flow rate. They will give you the relationship, but not the true condition. True condition is when the reservoir is going to pseudo steady state case, because most of the time reservoir produce under pseudo steady state case. For that purpose, we had done this extended flow rate. This, just a minute. Yeah, I'm in the lecture. Yeah. Okay, call you later. Lecture no, yeah. Okay. Yeah, taking lecture, yeah. Okay. So this extended flow rate is actual condition actually. So let's see, we can do the same thing. These are the 4 points with respect to pressure reference. We got the transient deliverability curve. They are not the actual one that I said. And now slope will remain the same. If you doing this analysis, the slope will remain the same. And in that case, you are having the 1 point, that extended flow rate. You put that point here. You can see here in this curve. This is the extended flow rate. Okay. This will be having the same slope as the other lines. Now the time you can choose. The time for each this kind of the things. Constant time you choose. Flow time. And you will be getting the transient curve using those flow versus pressure relationship, and actual conditions you can get just using this 1 point. Remaining things are same. This is your actual stability curve, IPR curve. This is the zero pressure conditions where you will get the absolute open flow conditions. In this test also, the limitation was that every time you are waiting at least till the pressure is reaching to the reservoir pressure again, correct? So the modified isochronal test is developed, or just simple modified isochronal test, where the time of the shutdown is reduced, means the time to reach the reservoir pressure is reduced. How it can be reduced? Let's say you are flowing, pressure drop will happen. When you shut down for a particular time, the pressure will go up. You don't wait till it is reaching to reservoir pressure. When you see like pressure has gone up little bit, you just start another flow rate. Pressure drawdown will happen again. You are having the same shutdown period. Another flow rate, shutdown period, flow rate, and then the extended flow rate. So do not yield again, this also not going to yield a true curve, but with this data you can obtain the transient stability curve, and extended flow rate data will give you the actual. The advantage of this is save time and money, because when you are doing the gas well testing, you are not producing with a full capacity. You are wasting your time, correct? You are not wasting time, means you are not having the business for that time. So, and time is also too much. Sometimes if it is a very tight formation, a reservoir, to reach the reservoir condition pressure, it may take several days. Okay, so it reduces time significantly. So diluvibility test, when should be done? First one, when the permeability is good, high permeability formation, do the conventional, because very quickly it will reach to the pseudo steady state condition. Isochronal, when the low permeability formations are there, you don't need to wait till the steady state, pseudo steady state condition, you can come back to the reservoir condition. And when the tight formation is there, achieving both the conditions will take long time, you can go with the modified isochronal test. Okay. Another approach to understand your reservoir is the decline curve analysis, where you plot some of the data and understand the behavior of the system, how the production is happening with respect to time, and in what manner the production will decline over the time. That can be understood with this. Another approach for the understanding this reservoir is the general material balance. It also called the tank model. So what happens? This is your reservoir. I said it is not that simple as it is shown in picture. It might be having any irregular geometry, irregular shape, and very heterogeneous in nature, where you are having this reservoir where you are having the oil, gas, water, and rock. 4 phases are there. Rock is also a substance that must be counted in the material balance because of its compressibility nature. It's also going to participate in the control volume of the system. Control volume is whatever the boundaries you define. Within that boundaries, these boundaries are filled with oil, gas, water, and rock. What happens? You are producing with this production well, oil, gas, and water. Okay, once you drill the well, you start producing all these 3. There might be a possibility water is getting influx in this reservoir from some nearby aquifer or some other places. Now you might be having a situation where you are having the injection well. So for example, you produce the gas, you inject this gas back. You produce the water, you can inject this water back into the reservoir. Correct? So this is a simple representation where gas and water can be injected back. The approach called the volumetric balance, since the volume of the reservoir is constant, the boundaries are constant, only it is occupied by the oil, gas, water, and rock, and change in volume of all those 4 must be equal to 0. When we produce oil and gas, what is happening? The change must be in the water and rock volume, same amount. Change in the volume should be reflected in the water and rock. That I said, the rock compressibility occupied the pores generated because of the production, because it was very under high pressure, but as the pressure release, the gas or the rock also expand and occupy those porous regions. So this tanking model, where oil, gas, water, and formation, F is formation of rock, you can just do initial and the final balance and you will get a good relationship. Just going a little bit fast. So you have to understand how much oil present was there, how much has been produced, similar for the gas, water, and what are the sources, external sources of water and gas in the formation. Some parameter need to understand because the gas is soluble in the oil. So you are not seeing the gas in the tank volume, but it is present there, it is soluble in the gas part. Okay, somebody again open up their mic. Any question? So whatever the initial volume, please mute. Somebody is Ranjan.
Yes, sir. Somebody has.
Can you ask somebody who's open? You can ask him by calling his name, his or her name.
Yes, sir.
No. Only I'm getting disturbed, so others also getting. So these four, the oil and gas, water and rock, their initial volume and their change in the volume. You can just account all of them, set up the system, you will get a good volumetric balance for the system. That will help you to understand how much gas, oil are present in the reservoir. This is the part that I was mentioning about value. Relationship can also be established. Simple. This is again flow through the pipe, correct? In a vertical direction. It might be at a particular angle also. The simple energy balance you will do. Only difference will be created because of this compressibility factor. Because this F is there. F is the friction factor. Friction factor depends on the temperature and pressure. Okay. It is a disturbance, Ranjan. Is
Request the participants to please mute the call.
whose call?
We are not able to find here whose call is muted here.
I can explain. Are you able to hear me?
Yes, sir.
Can you hear me?
Yes, sir.
Should I continue?
Yes, sir. You can continue.
दिन कुछ disturbance आ रहा है यार पीछे से.
I think now it's okay.
Okay, good. So I said like the flow through pipe is a simple balance, but you see here the velocity is there. Velocity means Q. Then you are having the fluid that is compressible in nature, fluid density, viscosity, they will vary as the pressure is changing and make the system little bit complex. And instead of getting a simple Bernoulli equation flow through pipeline, you get a complex equation in this. This is the only difference. Now solving this kind of the complex equation is a tricky part. Otherwise, the balance part to develop the WPR is simple one. Okay. So there are methods to do it. Kullender and Smith proposed one method. Average temperature and compressibility method are also there. Not going in detail. This is the choke device that I was saying. It is kind of a restriction on the top part of the surface. It is a restriction which will control the production. Okay. And there are variety of the choke devices are there, even electronically controlled. There could be nozzle types, orifice type. But the specific purpose of choke is control the production. Now, when the flow is happening through this choke, suddenly the area is reduced, velocity is increased, and velocity cross even sometimes the of the velocity of the sound. So you might be having the sonic flow or subsonic flow through this restriction, and the relationships are developed for that purpose. You are under sonic flow condition or subsonic flow condition. Again, you don't do much thing. You start with the mechanical balance equation, flow this through this choke device. Area is reduced, that you have to account it. Only problem is that we are dealing with the compressible gas. That's where the balance equations are a little bit complex. Now, based on the pressure drop across this choke device that you can control, you can decide or you can monitor you are under the sonic flow conditions or subsonic flow conditions. The important of this relationship, it can give you the control over or knowing some of the parameter by knowing the other. For example, Q can be calculated at given upstream and downstream pressure. Okay, or one of them can be calculated if others are given to you. So this is in summary about reservoir where we developed the IPR. We understood the gas well testing also here. Second was the WPR. Again, you do the energy balance equation like flow through pipeline. You get the WPR. On the top, you balance mechanical energy for the restricted flow. You got the CPR, choke flow performance relationship. Now I understand my production system from reservoir to valve to production. Now, what the individual does, IPR assess what is the potential of the gas production well. WPR, what is the achievable gas production rate through this valve. WPR is control the gas production rate. Now, these equations can together be analyzed using the nodal analysis. What nodal analysis is? It is a pressure continuity. See here, there is common thing. In the WPR and IPR, common thing is this pressure, PWF. In WPR and CPR, the common is this PHF, well head pressure. Now you can eliminate that, one of them using either the bottom hole approach, bell head approach, or this is bottom hole or bell head approach. You can eliminate one of them. Okay, so this is the way you just common factor taken out from the expression, and you got a little bit more complex, but only one equation. So one of the unknown can be taken out. Now, once this equation is there, you can use some optimization technique like Newton-Raphson or something to solve these equations. This is for the wellhead analysis, similar part. So this is where the production part is over. Now let's go quickly to processing part. I said processing part, you need to design several facilities at the surface itself before you're transporting them. So this section will talk a little bit about those surface facilities before transportation. So the oil and gas came to the separator, or from the separator you are getting it here. You can separate it in the oil phase. Gas phase will go to condenser where you are condensing the free water present in the system. Then it will go to the dehydrator where you will use some specialized techniques to remove the bound water, the water that is not able to be separated just by the gravity or simple method. Then remove contamination like H2S, CO2, they are the contamination in the natural gas. They are harmful, they are non-energy containing gases. If we are selling them, we are not generating any business. Because the business of the natural gas is in terms of the heating value of the natural gas. When you go to somebody to sell your natural gas, the first thing should be asked, what is the heating value your natural gas has? Because the heating value will depends on the composition of the natural gas. Okay, some important part can be, as I mentioned, propane, butane can be separated out before sending it natural gas to the pipeline, and those can be bottled and domestic supply purpose they can be used for the domestic supply purpose. So let's go one by one. Principle of separation is simple one. You need a gravity or centrifugal based separator that can separate gas liquid together, correct? Now there could be three-phase separator where liquid and water are also separated. Okay, Each separator should have some primary function, like it is separating the liquid from the gas, and then three sections should be there, like the centrifugal inlet. So you are sending the fluid here. It is having the large settling section where our fluid can separated fluid, like liquid will fall down because of gravity, and the gas will go up, and the gas still might be carrying some of the entrant liquid in it. So on the top you are having some mixed extractor or eliminator, that is just this kind of, the gas is hitting the eliminator and the entrant liquid is falling back to the bottom section of the separator. Separator could be horizontal, vertical, spherical. We are not going in that design. Dehydration process, very simple one. It is not that simple. Yesterday I was interviewing one of the GRF panel, and I asked very simple question: how you will remove the water from the gas? And the answer, what was the answer? Everybody thinks just heat it. Okay. While the reverse is required to remove the water from the gas, or the process called the dehydration. You can cool it. Once you are cooling, water will, the entrant water will separate it out from the gas. You can compress followed by the cooling. That's happened in our refrigeration system. Absorption and adsorption, they are the two standard chemical processes. In the absorption, you use the liquid that is having the affinity to the water. In adsorption, you use some solid like a silica. Those are having the affinity to the water. So when you are passing through the gas which is having the water in it, either the absorption tower or the adsorption tower, the water gets separated. Okay. A sweetening process, like removing the sulfur compound or the acid gases, CO2, CS, also the acid gases, they are very much important to remove because they are toxic in nature. If concentration is greater than 600 ppm of H2S, a person can be fatal in just 3 to 5 minutes. Okay, they are having the combustion product like the sulfur dioxide. Sulfur dioxide, they are responsible for these acid rains. They are corrosive to the metals when you are using in the transportation. For that all purpose, you need to remove them. They are unwanted. So simple. So sweetening processes could be direct conversion, absorption, physical absorption, chemical absorption. So a lot of processes are there. You can convert the sulfur compound into elemental sulfur. I think almost 30-40 process I know, those are designed for sweetening of the natural gas. They are classified like you are using the solvent, that is physical solvent, you are using some chemical solvent or hybrid solvent, you are generating non-regenerating adsorbent is used, or regenerating adsorbent is used. So similar absorption or adsorption process could also be there. So the gases are having the affinity to particular type of the solvent or particular type of the solid. We can fill the absorption adsorption tower, let the gas pass through it, and the solution solvent or the solid will extract or will absorb these gases on the surface. Again, then regeneration of those absorption column or adsorption column are required to perform for the economic point of view. Once natural gas is purified, everything is okay. You want to do the business, you have to understand how much volume you are producing, how much you are transporting, who is using how much volume. Of course, volumetric measurement is required. Standard orifice meter, venturi meter, these are the equipment, those are used for the volumetric measurement purpose. Natural gas transportation or also required compressor to be installed, and like our bottling plant, you to bottle this domestic gas in this cylinder, we need a compressor, correct? And the compressor of different capacities required depend on the composition of the gas, but the primary purpose of the compressor is to maintain the pressure. So if you are transporting the natural gas, you are collecting the natural gas from different sources. You are importing, you are collecting from your processing plant, some you are getting supply from other sources, whatever the sources are there. You put them in a trunk line, main trunk line, and you just send it to the consumer. Okay, within these two, what you do, you also having the underground natural gas storage or LNG plant. Why you have those two things? Because the natural gas is having the demand in the market different at different times. For example, weather-wise, in the Western world, people use the natural gas to heat their uh, houses, offices, or buildings. In summertime, it is not required. Okay, winter time, the gas is required to heat it. During that time, you can use some depleted reservoir where you are storing this natural gas, or you are converting it into LNG, liquefied natural gas. In all such cases, you need a compressor to compress the gas. Okay. Now, compressor design and the location of the compressor can be established based on the pressure drop is happening, and at what pressure we need the fluid to be discharged at the next level. The process of compression is not neither the isothermal process nor the adiabatic process. Sorry, isentropic process. It is somewhere the adiabatic process where the process happens. Analytical expressions or the diagrams like enthalpy entropy diagrams are designed to find out what capacity of the compressor should be chosen to compress the gas from pressure P1 to pressure P2. Of course, the composition of gases will play the role, because here you can see the K. This K is depend on the composition or the specific gravity of the gas. So volumetric efficiency and required horsepower can be calculated. Now I think the second last segment of the lecture, transportation of natural gas. So once gas is ready through the pipeline, it is pipeline means from the production it is put in the main trunk line. Now the responsibility to send it to the consumer. Now if consumer are not far, within a short distance we can lay down the pipeline. Okay, if quantity is too large, still the distance can be extended for several 100 kilometers, because it is a continuous supply. But if the distance is too large, it is not feasible to install the pipeline by geographical or geopolitical positions or business purpose, then you can still transport the natural gas in the LNG form. You liquefy the natural gas, you cool down the natural gas, convert it into liquid phase, and then transport it. You can compress it, because you can compress the natural gas, and then transporting in a small volume will be occupied. Gas to liquid, there are Fischer-Tropsch synthesis, other processes are there where you can convert gas into the liquid form, and then you are transporting it. Other means could also be there. Pipeline mostly account for 70% transportation, LNG is 30%, others are a small part of this transportation purpose. Same diagram that I showed you, you are having the supply from different places, you are supposed to send it to the consumer. Okay, you need to understand how to do this business. Okay, let's say you are going by LNG specific tankers are there. You need a LNG plant where you are transporting till LNG plant by the pipeline. You are converting into liquid by cooling it or compressing it, and then CNG and LNG are transported in a specific type of the container through the ship to other places. Or if you're just having the pipeline only for the entire length, then you need to understand the business of pipeline, how to establish the pipeline, what length, diameter, series, peddler combination of the pipelines should be chosen. Okay, again, simple, you are flowing the natural gas through the pipeline. There is no complex part in it. Okay, where the complexity comes? Because your natural gas is not ideal gas. Pressure drops happens because of the friction presence in the pipeline, and because of all those things you need to understand how we should design the pipeline, what diameter, length, and at what distance we need the compression station to be installed. Okay, so the equation becomes complex because of the non-ideal nature of the gas, but the equations are Behemoth equations, panhandle equation or modified panhandle equations. These are the three equations, those are decided. How those are designed? Very simple. That I said, you take a control volume of the pipe through which you are flowing, use the first law of thermodynamics, simple. This is the energy balance equations, pressure drop, gravity, friction losses, kinetic energy, I mean to say, and this is the this is kinetic energy, this is friction losses, and this is the potential energy. All three combined. Now solving this equation bring a lot of the things like the F, friction factor. Okay, what happens to this friction factor? This friction factor is a function of Reynolds number, roughness of the pipe, and other part. Reynolds number rho Vd by mu. It is a function of rho, function of mu, and those are the function of temperature and pressure. That's where the problem becomes very complex. This chart, this is a Moody diagram that also says like within this region, if you are not having low Reynolds number, even it does not depend much on the relative pipe roughness, correct? Or not depend much on the Reynolds number. But as the Reynolds number increases, you are having the large variation in terms of this relative roughness of the pipe, and that you need to include in it. So the difference comes how you are finding out this value of F. Different researcher gave different value. One gave just terms of diameter, another in terms of Reynolds number. Third one said why this coefficient A and B, my equation is also equally good when I'm having a different value of this numerical coefficient. Okay. So putting this in the simple equation, you will get this complex equation. This is d to the power 16 by 3. Others are constant kind of the things. Okay, panhandle, it is having a different relationship, and panhandle B, this will also be having a different numerical value of the powers. Certain assumptions were taken in this, just skip it. Now you are having the equation flow through pipeline. Why it is important to establish this relation? Let's say you are having the Behmeth equation. D is to the power 16 by 3 is the way the flow rate through a pipeline will vary. So if you are having the larger D, it is good. And length, with respect to length, it is a reverse relationship. If you are having a larger length, flow rate will reduce. So now job comes to find out good relationship between the length and diameter. For that purpose, you can design the series, parallel, and loop pipeline system. This is a series, different diameter. Not necessarily they are in increasing order, different diameter. This is parallel, one system, two system, three system. This is loop. Series parallel combination can be established. And once you do, you can find out if I'm having a single pipeline. Instead of that, I'm having a pipeline of a different length. So this is single pipeline of length L. I'm having L1, L2, L3. Those L1, L2, L3 equal to capital L of different diameter. What is the increase in the transportation of the fluid? The quantity that can be flow through the pipeline can be calculated for the series, parallel, and you will see in series it is just a relationship, length and diameter both are involved. Parallel, it is the same length will not be a factor, it is just a diameter only, and loop will include all of them. And this is the ratio that says like how much pipeline you are putting under the loop is the ratio of the diameter. One pipeline is replaced by the another pipeline. You can design n number of the pipeline system, and you can show your boss like I have done certain number of pipelines design. The cost will be another factor because depend on series, parallel you are having, but the throughput can be increased. So let's take one example. This is the case, 100% increase in the production. When I put 100% under the loop line, means I'm having the same diameter pipeline, I put the another pipeline parallelly, 100% increment will happen. But that's not the way pipelines are designed. You try to segment the pipeline, put the series and parallel combination to get the better throughput, and same time you're reducing the cost also. Of course, cost include other factors like material of construction, ball thickness, and corrosion alloys. This is what I was talking about, the transportation. This kind of the specialized tankers are there for the LNG kind of the liquefied. So you have to maintain the temperature. But the problem is that you put the energy here at the one terminal to convert the liquid gas into liquid, and then another terminal you need another energy to convert this liquid to gas. So it is very high energy intensive part. Just skip it. Other way could be convert the natural gas into syngas. From syngas you can get the lot of petrochemicals, or like even the petroleum fraction. Those are catalytical reaction like Fischer-Tropsch synthesis kind of the process. A lot of research has been done converting this methane into different fraction of hydrocarbons. So here what we do, we convert gas into the liquid, and that liquid can be used for different applications. Now gas to power, new ideas are coming. Our Prime Minister also announced, I think, in one of his speeches, Indian economy be shifting to gas economy, gas-based economy for power generation. So in the coal-fired power plant can utilize the gas if significant production is there and gas is having no other business. Gas to solid, gas to other commodity are also the part of that. Any question about it? Then I'll finish the last section of my talk. Any question, please? Okay, maybe we can have question after 12 also. So this we talk about the conventional natural gas. Let me give you some idea about the unconventional production of natural gas. So the simple definition of unconventional is which is not very well known. The technology is not well developed to be implemented by anybody. Okay, still you need very specialized skill to understand it, to implement it. That is unconventional. So tight gas, shale gas, coal bed methane, you might have heard these words. They are the unconventional source of the fossil hydrocarbon energy. Hydrocarbon, fossil natural gas. In terms of the amount available, you see the conventional is on the top here, but the volume is this much only. And on the bottom, we are having the gas hydrate. This is considered the vast amount of the gas hydrates are present on our Earth, and this volume is too much. It is at the bottom of this pyramid. And if it can be converted effectively to the gas, we are having a large resource of the gas on our planet. Okay. Some numbers are there, like different data for US and Canada, how much shale gas, tight gas, coal bed methane reserves they are having. Okay. So if you compare here the conventional versus unconventional resources, conventional is this color, unconventional is all these three combination. So you see conventional resources are bigger than unconventional resources are bigger than the conventional resources for many countries. Okay. North America has a much bigger portion of unconventional resources. Unconventional resources will change significantly with the data from other countries. So I am showing this data, I'm showing you for 2011. Sometimes data are provided, sometimes the accurate data are provided. A lot of the things here. You see here in this chart, India is nowhere. I don't know why that year India provided the data to this kind of the agency like US Energy Information Administration. They compiled this kind of the data that year. So depend on who provided the data, do they have accurate data or not. So the value may change, but trend is like the unconventional energy resources of natural gas are plenty on this planet if it can be exploited. What we will do with this gas, see here, this is in 2014 actual world energy demand, and this is projected in 2040. If you see here, the oil part 31%, oil is going to be reduced to 22% because the other sector of the energy are going to replace. Coal will significantly be reduced because of this lot of debate on this what it's called carbon environmental impact, the greenhouse effect and all those things, because coal are the most pollutant fossil energy source. These are the projected, actual we don't know. Nuclear is going to share a lot part, but depend on how people are going. These are projected, but what we can see, the gas is, if not going to downside in the fossil, it is at least the constant. While oil and gas, they are the other fossil energy, they are supposed to be less used compared to the natural gas. Natural gas is having a better future compared to oil and coal. Okay, Again, depend karega how the technology are getting developed to utilize this gas, like LNG and fuel cell technology. In fuel cell technology, what is required? Pure hydrogen, and this pure hydrogen can be produced through this natural gas. If that business is coming, natural gas will have in the bright future. Two more things I'll add here that is not part in this slide. First one, now people are looking for this hydrogen blending with the natural gas just to increase its calorific value. Okay, so if you get the hydrogen from somewhere, you use natural gas to improve with improving its calorific value. Second is, now as we are having this electric grid line, similarly now the concept is this, not now, since long it is there, sharing the gas grid. So if I produce some gas by other means, let's say pyrolysis or some other conventional mean, I can link my gas to that gas grid line, and I can make the business, and that's where the utilization of natural gas will also increase. Gas hydrates are everywhere, you see in this part, and plenty of reserve is there. This is considered the fuel of next century, that much quantity is present. This says like 5,000 trillion cubic feet of non-natural gas reserves worldwide in the form of gas hydrates are present. Gas hydrates are crystallized structure where the water molecules are trapping the light hydrocarbon molecules like this and forming a solid structure. This is, if you burn it, you will get the flame because hydrocarbons are there. The gas hydrate were actually the problem in the past, because if the temperature pressure is falling down, the water is there in your natural gas, they may create such kind of the hydrate and plug the pipeline. But now research has been advanced, we can prevent the gas hydrate formation. Sometimes we can explore where the naturally gas hydrate are formed underneath the seabed, from where we can get lot of hydrocarbon liberated out. How to get this out? This happens actually under high pressure and low temperature. So if your gas is having the water, low temperature and high pressure region, you will get the hydrate formation. So reverse you can do, you depressurize. If you depressurize the system, the gas will liberate out from this case-like structure. Thermal injection, you heat it, either sending the hot gas or by any means, you heat it. When you are heating it, the gas hydrate will be broken, gas will be liberated out. Use some chemical inhibitor, those are not letting the gas hydrate form. Okay, so it was a problem, or it is considered as a future of research. Coal bed methane, another form from where the natural gas can be extracted. So the coal seams are having the natural gas, those natural gas adhere to the coal bed can be replaced by some other gas, like for example CO2, and from where the natural gas can be produced. Depend again on several factors. Again, one more point is pyrolysis. I'll give you the example of oil shale only. So if you do the pyrolysis of any organic substance, you get the three phase: oil, gas, and solid. Now oil can be used for the liquid purpose, liquid fuel purpose. What to do with this gas? This gas is having the similar composition as the natural gas, that can also be considered after further refining to be used as natural gas is being utilized. This is about the where the tight gas are trapped, tight and shell gas. So shell gas are very unconventional reservoir where very tight formation is there, very small pores are connected and the natural gas are trapped. We need to create some fractures, increase the permeability or porosity, or break those kind of the structure through which the gas can come out. But a lot of research is required to have a controlled production of the research. Okay, so the volume of shale gas, shale oil reserve are massive. Advance in so everything depends on how economically and sustainable technology are getting developed. If it could be done for the shale gas, gas hydrate, other, the new age of hydrocarbon is expected yet to come. So I think towards the summary, just 5 minutes more are there. So the natural gas what is the future of natural gas industries? 19th century was the century of the coal. So first people started using the coal, and that's actually industrial revolution happened in Europe, and everywhere the coal was used to generate the energy. Then the engines came to picture, automobiles, and the 20th century was the century of the coal. That was the primary energy source to support the growth of global economy. At the end of the last century, natural gas took over the position of coal as the number 2 energy source behind the oil. It is expected the natural gas will be considered as a premium fuel of choice for the world economy in the future. Natural gas is superior to other energy in terms of the economic attraction and environmental benefits. Okay, natural gas production and demand is increasing. Primary producer of natural gas are US and Australia. Russia, Qatar, and ASEAN are the primary importers. China has increased. India also increased its natural gas significantly. But everything will depend. It's not just we are exploring where the natural gas is, whatever form it is, shale gas, gas hydrate, or other mean. Important is what is the utilization of that natural gas. Long time back, when the oil was found, natural gas was produced with the oil wells. People were not knowing what to do with this. They just let it go to the atmosphere. Then it came, okay, this might have some energy. Why don't use for the energy purpose? Then the street lamp were fired just on this. Okay. Later on, it was understood it might affecting the environment. The flare, it used to flare the just purpose. Okay, so the flue gas of the plant just flared. Okay, now we see the natural gas is having the value for lots of the purpose, but again economically viable sustainable technology, for example the fuel cell, converting into liquid gas, good pipeline infrastructure to transport from one place to the other place. It might be possible I have natural gas here, but I don't have any business here. But if proper pipeline infrastructure is there, I can sell it to some other places in the country or abroad, and those might be having the value. You might have seen this Ukraine and Russia war. Now entire Europe may be in a problem because there is a winter and their natural gas is being supplied by Russia to heat their houses. If that is stopped, they are in a problem. So Russia is having, for example, limited usage because their population is not that much. Europe is having a good business for them. So if good infrastructure could be developed, the natural gas may be the future for the hydrocarbon energy. Thank you very much. If you have any question, you can ask now, or you can send on this email ID, reservoir.itg@gmail.com. I prepare for this purpose only to discuss on reservoir and natural gas related questions. This is something else I just want to highlight. Some of the students, those graduated with me, they are working very good in their respective new positions. Ranjan Fukan is one of them here, who is doing good at Dibrugarh University. Mostly I'm doing research on EOR and pyrolysis part with several faculty in IIT Guwahati and outside from Dibrugarh. Dr. Samta Gogoi is also there. Tejpur University, Dr. Rupam, Oil India, Dr. Neeraj Mathur from University of Houston. I'm still in talk with Dr. Ganesh Thakur. This is just a summary of what I did so far. 6 PhD graduated, 2 books got published, and some 40+ journal publications are there. Okay. Yeah, thank you. Any question? Let me remove this. What should I say? How to remove, Ranjan? Should I want to come back to the video mode. What should I do? Yeah, it is here.
Sir, you can click the share screen, stop share screen.
I have to, what I have to do?
Stop share screen.
Okay. Let, okay.
Yes, sir. Yeah.
I can see. Beauty. So, how many participants are there? 104. Very good. 170 plus.
Yes, sir.
Yeah.
More than 100.
evening, I would like to take few questions. I could wind up within 2 hours. I was thinking it might be difficult, but just 2 hours I could finish it. Maybe I was rushing a little bit more, but you can go through the MOOCs course if you want in more detail. All the mathematical derivations with the examples are solved there. But if any specific question you have, I would like to take that question. I don't know I'll be able to answer or not. Sometimes some question comes, I don't have to answer. But I would like to take the questions. So please.
Yes, sir. Sir, there is a question in the chat box from Vijay Singh.
Yeah.
The question is, sir, can you describe how to measure the sulfur content of oil sample? What test we use for measure inorganic or organic sulfur measure?
Yeah. So I'll read the last line. What concentration you say sweet or sour? Yeah, exact value I don't know about the oil or the gas also. But if it is smelling, means the objective is to remove as much as you can. There is, I said, less than 600 ppm or greater than 600 ppm is fatal. In fact, in the natural gas, it is 4 to 6 ppm that is allowed in the natural gas to sell it to the end users. If above that it is there, should be considered as a sour gas. You are supposed to remove that. There are several well-established correlations are there to measure the sulfur content in the natural gas. Exactly, I don't have any particular method name in my mind where I can say, okay, using this method you can do. But I do for the solid CHNS analysis, I do for this liquid also, the ultimate analysis, correct? Where we measure the carbon, hydrogen, nitrogen, sulfur. Distinguishing inorganic and organic sulfur compound, you may separate out the organic fraction from the inorganic fraction, and that's where you are measuring the separate the sulfur compound in both these samples. Exact name I don't remember the method name.
Thank you, sir.
Could you please explain unit system in slide 9? The image representing separator gas in slide 10 and 11. Which slide it is? This is unit system in slide 9. The images. Can you please, Sanghamitra, if you're talking about the unit system that I said, unit are different for the petroleum reservoir engineers. Petroleum reservoir engineers include the gas engineering also, even all drilling, production, processing, they are all petroleum engineer. The unit system in the practice is US unit field system, where you have to compile a list that I said. We all know the area could be measured in meter square or kilometer square or something, but they measure in acre. Similarly, the distance is measured in feet. Similarly, the volume of the gas is measured in standard cubic feet. Volume of the liquid or oil is measured in standard tank barrel. So there is a barrel of a particular size. That barrel also varies in UK and US, but you are having a standard tank barrel. You measure the volume in that. So the field unit system you need to understand. You cannot just simply start as a chemical engineer. You have to adopt something to become the petroleum engineer. That's why it's on that slide, where one of the foremost thing is understanding the unit system. Would you please let me know that why ONGC stop working of shale gas? Yes, so shale gas is not easy to explore. Okay, even though if we find out there is a large resource of the shale gas in a particular region, getting it out from those tight formation is a very tricky job. Laboratory experiment cannot be performed so precisely for that purpose. Mostly you depend on the computer model, because in computer model you create the geometry with the non-parameters and you start creating the fractures. Those fracture could be with the hot fluid, could be propellant or by blast or something. But how effectively you can do it, you don't know. Plus, these are the tight formation. You might have taken sample from somewhere. You are seeing, wow, there is a plenty of shale gas there. The nearby section might not have any. Okay, so there is a lot of heterogeneity there. Ultimately, any company is a business profit making company. The simple answer to your question could be they might not be making a good business. They might not be having a good technology to exploit or explore the gas from the shale formation. That's why they might have stopped it. What is the future of India in shale gas? Yeah, we are having the shale gas reserve, Kaveri Basin gas reserves are there, but any future will depend how world, not only in India, how world is developing the technology. Okay, a lot of the technology in India we use even for different sector, we imported them from abroad, and we are doing a lot of production or manufacturing in India. If in India or abroad good utilization of natural gas is established, then only it is having the value, whatever it is, shale gas or any type of the gas from different sources there. Okay, so the future will depend. Nowadays, that I said, even 3-4 decades back, people were not talking about the natural gas. Now people are talking about natural gas. Our ministry or Department of Science and Technology, they are having the special project call on how to deal with natural gas for effective utilization. Recently, I got one meeting with OIL. Now they want, can you blend hydrogen with the natural gas to improve the calorific value or the properties of the gas? So depend on how effectively the technologies are being exercised, developed and exercised, the future will be bright. But yes, compared to the other fuel, it has been realized natural gas is much safer, cleaner, and it is having the good future. Because a lot of reserve is also available in the form of shale gas, gas hydrate. 30 years back, nobody was knowing about the shale gas hydrates, correct? 30, 40 years back.
Thank you, sir.
Any other question?
Other questions?
Thank you.
On behalf of everyone present in this program, I want to thank and appreciate Professor Pankaj Tiwari sir for his insightful and interesting presentation on the important topic of natural gas engineering. We found the presentation very systematic, informative, and enlightening, and we believe everyone felt the same. Sir, your lecture covered most of the important aspects of natural gas engineering, and I hope participants were greatly benefited. It was a pleasure listening to you, sir. Once again, from Dibrugarh University, we thank you, sir, for accepting our invitation and speaking to us today.
Yeah, thank you very much. Thank you for everyone for joining this session. And if you have any question, I said reservoir.iitg@gmail.com email ID where we can discuss. Okay, thank you very much. So should I sign out?
Yes, sir. So now we will take a break of 30 minutes before we join for the next session at 12:30 p.m. Please join again for the next lecture on drilling fluid technology by Dr. Borkha Mek of Dibrugarh University. Thank you all.
Thank you.
Is it audible? It is my pleasure to introduce our.
Actually, can't hear you. Hello, am I audible?
Yes, yes. It is my pleasure. It is my pleasure to introduce our resource person for this session, that is the second session of today, Dr. Borka Mack of Dibrugarh University, who is going to talk to us on drilling fluid technology and its effect on the answer. Dr. Mack is presently working as an assistant professor in Department of Petroleum Technology, Dibrugarh. She has around 13 years of teaching experience as a professor. She has done her BTech in mechanical engineering from from Jorhat Engineering College, and then did his master degree in the Department of Petroleum Technology from Dibrugarh, and she received her PhD degree in Petroleum Technology from Dibrugarh University in 2000. He is also faculty advisor of Society of Petroleum Engineers and Federation of Indian Petroleum Industry, Dibrugarh University Student Center. Under her guidance, Society of Petroleum Engineers, Dibrugarh University Student Chapter has been awarded Student Chapter Excellence Award. That is the biannual membership retention award and 10-year milestone anniversary. He is an active member of Society of Petroleum Engineers International and also serving as a mentor of Society of Petroleum Engineers in mentoring program. He has 17 numbers of publications, journal publications, national and international. Then 5 conference proceedings is also there, and 10 book chapters is also he has published, and he has also published one book. He has received Young Researchers Award 2020 by Institute of Scholars and ISO 9001-2015 certified institute by International Accurate Certificate accredited by UASL. He has reviewed many papers of printers, journals, and her area of expertise includes enhanced oil recovery, drilling fluids, environmental technology, oil logging, and geophysics. So please join me in welcoming Dr. Borka ma'am. So over to you, madam.
Thank you so much for this lovely introduction of mine. So, have you made me presenter? So that I can start with the presentation.
Yes, now you can share your slide.
Yes. Can you see my slides?
Yeah, yes, yes. It's all right. You can go for slide now.
Uh, Is it fine now?
It is fine.
Actually, good afternoon to one and all present here. First of all, I would like to thank Dr. Ranjan Fukan and Mr. Prasann Vadi for giving me this opportunity to speak in this faculty development program on recent trends in upstream petroleum technology under AICTE. So it's a great pleasure and honor for me to be here with you all today. So today I will be giving a lecture on the topic that is drilling fluids technology and its effect on the environment. Just can you tell me one thing? Actually, one page is coming here. I'm not being able to see my presentation on it.
Regarding slide, it is okay. That is, you are unable to see your own slide, or
Yes, just give a few minutes. Anyways, let me continue. Okay, so today I will be giving a lecture on drilling fluids technology and its effect on the environment. So basically, we know that drilling technology, it is generally drilling a borehole so that we can reach a target depth to produce hydrocarbon which is present in that depth to surface. So I am not going to tell about the drilling technology today, but I'll be telling about a very important component which is related to drilling technology. That is drilling fluids, its technology, and its effect on the environment. So starting with what is this drilling fluid or drilling mud system? So this drilling mud system is the single and most important component of well construction process, without which a drilling operation is almost unthinkable. So drilling mud system, it is actually designed and formulated so as to perform efficiently within the expected wellbore conditions. And an active drilling mud system, it comprises of a volume of fluid which is being circulated and pumped through the specially designed mud pump. It is allowed to flow through the drill string exiting at the bit and through the up the annulus to the wellbore and back to the surface. For solids removal in maintenance treatments as required. So the fluid which is being circulated in this system, that is known as the drilling fluid, and it is a circulatory fluid which helps in carrying out a cost-effective and efficient drilling operation so as to reach the target depth with minimum possible damage to prospective formations. So if you want to define drilling fluid, it is actually a circulatory fluid which is used in rotary drilling so as to perform any or all of the various functions which are required to have an efficient drilling operation. So we have various functions of drilling fluid, like control formation pressure. And basically what happened in the subsurface, we may have, while drilling, we may encounter high formation pressure or we may encounter low formation pressure. So if it is high formation pressure, we should try to maintain a high hydrostatic head so that it will be able to suppress the high formation pressure. And if it is low formation pressure, then we should have hydrostatic head in such a level that it should be compatible with the formation pressure. And we can manage this hydrostatic head by managing the density of the drilling fluid. So if we can have a proper density, high density, we can have high hydrostatic pressure to control the high formation pressure. And if it is low density we have maintained, it will be beneficial to be compatible with the low formation pressure. Then next is cooling and lubricating the bit. So basically, when the drilling operation it goes on, drill bit, we can see in this picture drill bit, it basically cut the rock particles. So while cutting the rock particles, excessive amount of heat is generated. And whenever the drilling fluid will circulate, it will dissipate the excessive heat which is being generated, and it cools the drill bit and the drill string. And it also helps in lubricating the drill bit so as to reduce the torque and drag. Then we know that while drilling is going on, different amount of cutting particles will be generated. That is a rock cutting particles. So drilling fluid, since it is a circulatory fluid, it will help in cleaning those cutting particles which are generated and then transporting those cutting particles to the surface. Then whenever the drilling fluid will circulate, then it will lead to the formation of a filter cake, and that filter cake, it helps in stabilizing the wellbore, and it also allows adequate evaluation of the formation. Generally, after drilling, we send a certain sensor. That sensor is known as the logging tool, and that is basically used to evaluate the properties of the layers of the formation subsurface. And it has to be sent, or the drilling, or you can say that logging tool will be, passing through the drilling fluid. So we should design and formulate the drilling fluid in such a way that it should allow the logging tool to evaluate the properties of the formation. So these are the various properties of the functions of the drilling fluid which are basically required so that we can have an efficient drilling operation. Just wait a minute. I don't know what is problem going on with this. Can you just help me?
Yes, ma'am.
Yeah, actually what happened, some page is coming in the presentation slide. I'm not being able to see my slides.
Ma'am, here your slide is visible to us. And there is nothing coming over in your slide. I guess other participants are also not facing any problem.
Yeah, but one box is coming. It's actually making me difficult to, because some diagrams are there. I wanted to show with the help of those diagrams only, but I'm not being able to. Just wait a minute.
Yes, ma'am. In the presentation slide, something is in the downward, something is just cut out. But now it's again already.
Can you see my slides now?
Yes, ma'am.
So is which number slide is coming?
4.
Slide number 4.
Okay, thank you so much. I think it's slide number 5 now.
Yes, ma'am.
Okay. Sorry for the inconvenience caused. So these are the various functions of drilling fluid. So basically these functions are required to be maintained by the drilling fluid so that we can have an efficient drilling operation. So what will be a common drilling fluid comprises of? So basically it's a continuous phase. To that continuous phase, we add reactive fractions, then inert fractions and chemical additives. Reactive fractions are added so as to provide, viscosity, a certain viscosity to the drilling fluid. Then inert fractions are added so as to provide the required mud weight. Then chemical additives are added so as to maintain the mud properties. So depending upon what is the continuous phase we will be using, then depending upon what is the type and concentration of reactive fractions, inert fractions and chemical additives, we have different types of drilling mud. So we have different types of drilling mud, which has been mentioned over here. That is pneumatic drilling mud, then water-based drilling mud, oil-based drilling mud. So this pneumatic, water and oil-based drilling mud, these are the conventional drilling muds. And above these conventional drilling muds, we have synthetic drilling mud and non-damaging drilling mud. So which are kind of a replacement to some of the conventional drilling mud. The basic difference between these different 5 types of drilling mud is the continuous phase into which your mud has been prepared. So pneumatic drilling mud, the continuous phase is dry gas or air, and to that dry gas or air we add different other additives and chemicals so as to reach the desired properties of the drilling fluid according to the characteristics of the formation. Next is water-based mud, where the continuous stream is water. To that water, the first component which we add is clay, and after that we add different other weighing materials or chemical additives so as to reach the desired properties of the drilling fluid according to the characteristics of the formation. The next is oil-based mud, where the continuous stream is oil. To that oil we add water. And if you want to mix oil and water to form a stable emulsion, it is required to add different emulsifying agents and different other additives so as to reach the desired properties. Next is synthetic drilling mud. So synthetic drilling mud is a replacement to the conventional oil-based mud, because oil-based mud to some extent is actually creating toxicity to the environment. So in order to avoid that, instead of using conventional oil-based mud, we go with the use of synthetic drilling mud. The next is non-damaging drilling mud, which is a replacement to the conventional water-based drilling mud, because in water-based drilling mud, as I've mentioned, the first component is clay, and after that we add different weighing materials like barite. But this clay and barite, they actually cause damage to the formation. So again, in order to avoid that, we generally go with the introduction of one kind of a mud which is free of clay and barite. So that kind of a mud is known as non-damaging drilling fluid. So these are the different types of drilling fluids which are basically used in oil industries. And if we are going for a drilling operation in a specific well, then the factors which basically decide like what kind of a drilling fluid we should use, that is first is definitely cost. we need to determine what will be the cost of the drilling fluid that we will be using. Then second is whether that drilling fluid is capable of giving optimum technical performance or not. Then next is the most important, that is the environmental impact. So whether the drilling fluid which we will be using, which we have formulated, is environment friendly or not. Then there's one more thing, that is safety. So there's cost, technical performance, environmental impact, and safety. These are the four key factors which basically help in deciding the oil industry people to take what kind of drilling fluid for their drilling operation. So come to the components of drilling fluid. So in brief, I have already mentioned that if you want to formulate a drilling fluid, it is basically, we'll be having continuous phase. To that we'll be adding reactive fractions, then inert fractions, and chemical additives. And this is in bit details, like what components are generally added so that we can have the desired properties of the drilling fluid. So these are like viscosifiers, weighing materials, then chemical additives, emulsifiers, loss circulation materials, then fluid loss reducers, and some special additives. Viscosifiers, like everyone knows, it is used to increase the viscosity of the drilling fluid. The two most important viscosifiers which are added in drilling fluid, these are clay and polymers. Then weighing materials are basically added to increase the density of the drilling fluid, like we can add barite, calcium carbonate. Then chemical additives are basically added to enhance the rheological properties of the drilling fluid. And two most important chemical additives which are being added, these are mud thinners and mud thickeners. So mud thinners, which are basically used to reduce the viscosity, and mud thickeners which thicken the mud, that means it increases the viscosity. Then we have emulsifiers, which are generally used in oil-based mud. And we know that if you're preparing an oil-based mud, it is required to add water. And in order to have a stable emulsion, we add primary emulsifiers, or if more stabilization is required, then we go with the addition of secondary emulsifiers. Then we have loss circulation materials like granular, flaked, and fibrous materials, which are generally added to plug the pore spaces or the fractures which are present in the formation, so that we can prevent the loss of drilling fluid to the formation. Then we have fluid loss reducers like CMC, emulsified oil, gilsonite, which are again used to enhance the filtration properties of the drilling fluid. And apart from these general components, we have certain special additives also which are required for very special and specific purposes, like corrosion control additives, defoamers, then pH control additives, mud lubricants to enhance the lubrication to reduce torque and drag, then anti-differential sticking chemicals to prevent the stuck pipe situation. So these are the various components of drilling fluid. And if we want to formulate a drilling fluid, we should always try to choose the optimum concentration of these components so that we can have, or we can achieve, the desired optimum properties of the drilling fluid. Because again, optimum properties of drilling fluid is required so that we can have an efficient drilling operation. These are the important properties of drilling fluid, like density. Density is very much important to control the formation pressure. Then rheological properties, which basically helps in cleaning and transporting the rock cutting particles to the surface. So it basically manage the flow properties of the drilling fluid. Then we have different types of rheological properties like plastic viscosity, then yield point, gel strength. Plastic viscosity, that is the internal resistance which is created because of the presence of solid particles in the drilling fluid. And yield point is the measure of force that causes the mud to develop a gel-like structure if it is in motionless condition. And gel strength, ability of a mud or drilling fluid to develop a gel-like structure, again if it is in motionless condition. Then filtrate loss, that it basically deals with the filtration properties of the drilling fluid. So it again leads to look into the flow property of the drilling fluid, whether the drilling fluid is being able to flow without getting lost to the formation or not. Then apart from these, yes, am I audible? Okay, so other properties are like solid content and pH, which are again related to the flow properties of the drilling fluid itself. So I just would like to give in a bit details related to the different types of drilling fluid which are used in drilling industry. So which I have already listed, that is pneumatic mud. So here the continuous stream is air or gas, and we generally have either air, we may have we can use natural gas, inert gas, or it may be mixtures with water. So based on that only we have different types of pneumatic mud also, like dry air or gas, then we have mist or foam mud, then we have aerated muds also. Now this pneumatic muds are basically used in those areas where there is little chance of encountering water, or we can say that it is economic in those areas which are basically known as the hard rock areas, and in those areas where we generally have low formation pressure and where loss circulation is a major problem. That means loss of drilling fluid to the formation is a major problem. So in those areas, use of pneumatic mud, it helps a lot. It helps in minimizing the formation damage also, and it also helps in increasing the penetration rate. That means the rate with which the drill bit will penetrate and cut the rock particles. Then we have water-based mud. So here the continuous stream is water, and to that water the first component that we generally add is clay. So clay, it gives the initial shape to the drilling fluid, and basically if we add a bit smaller amount of clay also, it helps in enhancement of the properties of the drilling fluid to a very high level. And if clay is not enough to reach our desired properties, then then only we go with the addition of different other weighing materials, viscosifiers, and other chemicals. So clay being a first component of water-based mud, which is the most commonly used mud in oil industry. So this clay mineralogy, it actually plays a very important role. So clay, everyone knows what is this clay. This is a naturally occurring material. It's a fine-grained minerals which can be hardened whenever it is required by drying or firing. So this clay deposits, they are basically composed of clay minerals like phyllosilicate minerals, and it's a very it has very general uses. Like it is not only used in petroleum, everyone knows it has very general uses like in agriculture, in ceramics and construction. In the same way, it can also be used in petroleum industry, specifically in drilling industry. So this clay, these are very small size particles which is less than 2 microns, and it has large surface area. Since it has large surface area, this is the most important reason why a very small amount of clay, it helps in enhancing the properties of drilling fluid to a very higher level. It carries a negative charge, and if we talk about its structure, it is basically phyllosilicate structure. That is, phylon means leaf and silic means flint. You can see in these pictures, these are some microscopic pictures. So each clay particle, you can see these are some kind of leaf-like structures. So structure-wise, it is known as a phyllosilicate structure. And we know that clay minerals, they're generally present in the earth crust. So how does clay minerals originate? So it's a very general phenomena that whenever your rock, it comes into contact with water, basically if it is acidic water, it converts rock into clay. Water, it becomes acidic when carbon dioxide, it comes into contact with water. It leads to formation of carbonic acid, which will again form hydrogen ion and bicarbonate ions. So just take an example of a rock, that is your feldspar. So whenever feldspar, so whenever this feldspar, it comes into contact with this acidic water. So that means it is coming into contact with the hydrogen ion. So hydrogen ion will displace this silica and potassium ions, and it leads to formation of another substance that is known as kaolinite. And kaolinite is a type of a clay mineral. So this is how like feldspar, which is kind of a rock, when it comes into contact with acidic water, it changes, like it gets changed changed from rock type to a kind of a substance which is a type of a clay mineral. So feldspar is getting converted into kaolinite, which is type of a clay mineral when it comes into contact with acidic water. So this is how clay minerals are formed, and they are present in the earth crust. Now we have different types of clay minerals, but whatever is the type of the clay mineral which is found in the earth crust, the basic structural unit or the basic building block is this, that is silicate tetrahedron and aluminium octahedron. And generally we have 4 types of clay minerals, and almost all clay minerals, they're made up of these 2 fundamental crystal sheets, which are again formed by your these 2 building blocks, that is silicate tetrahedron. This is one molecule. This is one molecule. Where is my cursor? Okay, this is one molecule of silicate tetrahedron, and it, several molecules combine together, which leads to the formation of this tetrahedral sheet or silica sheet. Then we have next is the aluminium octahedron. Again, several molecules lead to formation of your, we can see that's a gray sheet, that is your octahedral or alumina or gibbsite sheet. So we generally have, as I mentioned, 4 different types of clay minerals, that is kaolinite, illite, fluorite, and montmorillonite. So I just would like to show you the characteristics of these 4 different types of clay minerals, and from the characteristics only we can analyze like which clay mineral will be beneficial for the formulation of drilling fluid, like kaolinite. So kaolinite is what? That is mineral which is made up of silica and gibbsite sheet in a ratio of 1:1. So here we can see that, just give me a minute. Okay. So we can see here that this is one, silica sheet and one gibbsite sheet. So this is a 1 unit of clay particle, and 1 unit of clay particle, it is getting bonded with another unit. So in this way, the entire clay mineral is being formed, and the ratio of 1 unit of clay is 1:1. That is 1 silica sheet and 1 gibbsite sheet, and the 2 units, they are bonded together by a hydrogen bond, which is very strong bond. So if we use this kaolinite for the formulation of drilling fluid, what we will do, we will put this kaolinite mineral into water. So water will try to get absorbed over the surface of the clay crystal, and also it will try to enter into the interlayer separation between the 2 units. But since the bonding here is very strong, so water is not allowed, water molecule is not allowed to enter into the bonding, or I can say the interlayer separation between the 2 units. So since it is not allowing water to get enter inside it, it is just getting absorbed over the surface. So this is kind of a more stable mineral, and it has little expansion if it is put into water also. So it is kind of a least active mineral. Then we have illite structure. So this illite structure, here we have the ratio of 2:1. That means 2 silica sheet and 1 gibbsite sheet. And the distance between 2 silica sheet is 10 degree Armstrong. And the bonding which is present between 2 unit is potassium bonding, which is, one of the second strongest bonding after hydrogen bonding. So same phenomena, if you put this illite mineral into water, then water will try to get absorbed over the surface, as well as also it will try to enter into the interlayer separation. But since the bonding is very strong, it is not allowed, and again this is also kind of a least active mineral. Then another is a chloride mineral, and chloride mineral is again 2:1 phyllosilicate mineral. So here the interlayer space is occupied by some stable positively charged octahedral sheet. So this is also non-expandable, and it shows minimum swelling. So this is kind of a different kind of a mineral which is green in color. We also call it as a green mica, and this is very soft kind of a mineral. If you scratch it by your fingernails also, some kind of powder will be generated, which will be green in color, and if you rub between your fingers, it feels like an oil. So oily, as if you are touching some oily substance. So this is chloride. Again, this is also minimum swelling is will be there if you put it into water. The next is Montmolonite structure or Montmolonite mineral. So this is also 2:1. We have 2 silica sheet, 1 gibbsite sheet as 1 unit, and the distance between 2 silica sheet is 10° Armstrong. And by van der Waals forces, which is a very weak bonding. So since the bonding is very weak here, if you put this Montmolonite mineral into water, then water will get absorbed over the surface as well as it will get a chance to enter into the interlayer separation. Since it get a chance to enter into the interlayer separation, so it has high volume change and it also swells more. And its opposite is also there, like if in presence of water it shows high swelling. In the same way, in absence of water there will be more shrinkage also. So what we can see that if we put water into the Montmolonite mineral, there will be high volume change and more swelling will be there. So we have discussed 4 clay minerals, that is kaolinite, illite, fluorite and Montmolonite. And among the 4 different types, we have observed that Montmolonite is one of the mineral which is showing high volume change and it is allowing more water to get absorbed and it swells also more. So since it swells more, high volume change is there. So if you put this Montmolonite mineral into water, it leads to enhancement of the properties of the drilling fluid a lot. So if you do a comparative analysis between all the 4 different types of clay minerals, Montmolonite mineral, it plays a very important role, and this is the only mineral which we can use as a clay for the formulation of our drilling fluid. And the mechanisms and factors which are associated, which are the basic reasons why Montmolonite is showing better enhancement in the drilling fluid properties. It is because it has more ion exchange capacity, then it has more swelling characteristics, then it has the capacity to form electrostatic double layers. So these are the various factors or mechanisms which makes Montmolonite a better clay mineral for the formulation of drilling fluid. So that is the first component of water-based drilling mud. If we want to form a water-based, as a first component, we add bentonite, which is a type of a Montmolonite clay. Because Montmolonite clay, it is found in its purest form in the name of bentonite. So come to the classification of water-based drilling fluids. So we have different types like non-inhibitive mud, inhibitive, polymer, and emulsion mud. Non-inhibitive mud that we have discussed now, that is the very simple and inexpensive type of a mud which comprises only water and clay. So that water and clay, or you can say simply as water bentonite mud. So that is a type of non-inhibitive mud. This is very simple and inexpensive type of a mud. But it has certain drawbacks, like it cannot be used in those areas of formations which are type of unconsolidated formations or dispersive formations, because they can have certain formation damage. So instead of using non-inhibitive mud, we can go with the use of this inhibitive mud, where we have water and bentonite definitely, but along with that we have certain various other chemicals or additives also. And based on what chemicals or additives we are using, we have different types of inhibitive mud, like calcium mud, potassium mud, salt saturated mud, then MMH, that is mixed metal layered hydroxide drilling fluid. So here the mixed metal layered hydroxide, that MMH particles, these are very extensively small type of particles. They have multiple positive ions and they can be associated with bentonite, and it also helps in minimizing the formation damage along with the enhancement of the drilling fluid properties. Then we have polymer mud, where we are using specifically polymers as a main component for the formulation of drilling fluid. And using a polymer, it helps in increasing the rate of penetration, then enhancing the properties of the drilling fluid. It also minimizes the formation damage. And a very important thing is that its operation and transportation cost is also less. Next is emulsion mud. So emulsion mud, that means it will be either oil in water or water in oil. Since it is a water-based mud, so it will be oil in water. Addition of oil in water, it again leads to various advantages, like it enhances the lubrication, improves the lubrication, reduces torque and drag. Then it increases the rate of penetration. It also improves the loss circulation problems. So these are the different types of water-based mud and their applications depending upon the characteristics of the formation. The next come to oil-based mud. So oil-based mud, here the continuous phase is oil. To that oil we add water, and again if you want to form a stable emulsion, we add emulsifiers, wetting agents and gellants. Oil which is being used here, it may be either diesel oil, kerosene oil, fuel oil, or some selected crude oil or mineral oil. And the water which is being added, it may be either fresh water or saline water. Then there are basically two types of oil-based mud. One is oil mud and invert emulsion mud. And the basic difference between the two mud is that oil mud is a true oil-based mud. That means we have maximum portion of oil, and to that oil we are just adding less than 5% of water. And invert emulsion, that means we are adding water up to 50%. And both the oil mud and invert emulsion mud, they have the same advantages, like they can be used in pay zone areas where there is every chance of having formation damage with the use of water-based mud. Then we can use this oil-based mud in some troublesome shale formations. Then they are very much temperature stable, so they can be used in deeper wells where we have high temperatures. So these are the important advantages of oil mud and invert emulsion mud. So we can say that if we do a comparative analysis between oil-based mud and water-based mud, so oil-based muds are much more advantageous in many factors, like it can be used in troublesome shale formations because it prevents the shale instability problem. Then it will create a thin mud cake, which again reduces the risk for pipe stuck situation. Then it provides lubrication. Then we have vast improvement of scaling and corrosion problems. So these are the various advantages of oil-based mud. But uh, though I have mentioned many advantages over water-based mud, but its use is limited because of two main problems. First is oil-based mud, these are very much costly. And second thing is that the most important thing, that oil-based mud, they generally have an hazardous effects to the environment. So because of these reasons, generally use of oil-based mud is very much limited. We have various disadvantages. Some disadvantages I have listed over here, like inability to analyze oil shows in cuttings. Now, we know that whenever the drilling operation took place, cutting particles are generated. So those cutting particles are taken out by the drilling fluid to the surface. And those cutting particles are actually analyzed so that we can have evaluation of the properties of the formation of the, from the depth from where the cutting particles has been come up. So if we do the analysis of cutting particles, we've been able to find out the important properties of the formation. So cutting particles also plays a very important role. And along with those properties, we can also determine if oil or hydrocarbon is present in that particular depth or not. Basically how it is done, cutting particles are generally, once they have come up, we take those cutting particles and put it in a kind of an instrument which is known as a spook box. So if you put those cutting particles in the spook box, a fluorescence, if a fluorescence is observed, so that fluorescence, it shows the presence of hydrocarbon. If we are being able to see some kind of fluorescence, it shows the presence of hydrocarbon. So this is basically, specifically used for water-based mud. But if it is oil-based mud and the cutting particles that has come up, we have put it in the spook box, so definitely we'll be able to see some fluorescence. But that fluorescence, we will get confused that fluorescence is because of the hydrocarbon which is present in the subsurface, or it is because of oil which is present in the mud. So if it is oil-based mud, we cannot analyze the cutting particles to determine the presence of hydrocarbon in the subsurface. then we cannot have the real determination of API gravity also because of the contamination of oil with the cuttings and core samples. And the most important disadvantage that it has various environmental hazards. It may contaminate the areas of freshwater aquifers. Then disposal of cuttings in an appropriate place again may lead to certain environmental contamination. So these are the various disadvantages of oil-based mud. Although we have various advantages, its use is limited because of these disadvantages, and the most important disadvantage that it has various environmental hazards. So the main problem here is the oil which is generally used in this conventional oil-based mud. So people started thinking of why not to replace that conventional oil by some other oil which are less toxic to the environment. So the oil that we can use or we can replace the conventional oil by the synthetic oils like linear alpha olefins, internal olefins, polyalpha olefins, esters, ethers. So these are some kind of oils that we can use as the continuous phase, and the mud that we will be getting, that is known as a synthetic based mud. So this is the mud which can replace the conventional oil based mud. So here the continuous stream will be synthetic oil which is almost free of the aromatic content. So basically what is the problem with the conventional oil is that the conventional oil which we generally use is basically it has aromatic content of the hydrocarbon, and aromatic content of the hydrocarbon is the main reason which is creating toxicity to the environment. So if we can use such kind of mud, or you can say such kind of oil as a continuous stream where we have tried to remove the aromatic hydrocarbon, or we can also use some mineral oil with less than 1% of the aromatic content. So those kind of mud will be more environmentally acceptable than the conventional oil-based mud for use in both onshore as well as offshore drilling operations. And the cutting particles which will be generated, they can also be disposed of into water because they biodegrade faster and they will have less toxicity to the environment. Although the cost of synthetic based mud per barrel is very high, but since they have fast rate of penetration and less mud related non-productive time, it makes them more economical choice to be used specifically in offshore drilling operations. And if we talk about its advantages are almost similar to that of your oil-based mud. I've listed various advantages, the same advantages we have from the SBM mud also, with an added advantage that it has less toxic effect to the environment. The next is non-damaging drilling fluid. So this is a replacement to the conventional water-based drilling fluid. As I have mentioned that in conventional water-based drilling fluid, we add clay as the first component, then we add barite. So this clay and barite, they actually cause damage to the formation. And specifically, if we talk about the pay zone section, that means the main reservoir sections from where hydrocarbon will be produced to the surface. So basically those conventional mud, they create damage to the pay zone sections. So specifically for the pay zone sections, and also in those sections where formation damage can easily took place because of the characteristics of the formation, non-damaging drilling fluid, a kind of a drilling fluid which is free of clay and barite, will be most suitable. Now there are various mechanisms that attribute to formation damage that I just would like to show you. Like in conventional mud, we have clays, we have barites and all. So these are these are the fine solids. So these fine solids, they actually lead to formation plugging, and there will be hydration of clay and plug around the pay zone by the filtrate. Then we may have change of wettability by the filtrate. Then we may have mud invasion into the pay zone due to loss circulation. Also, we may have formation of scales due to chemical reaction between formation fluid and mud. So these are the various mechanisms that will attribute to the formation damage whenever the conventional drilling mud, it flows and circulates through the annulus coming in contact with the wall of the borehole. So what can be the solution? solution, what solution we can adopt. So what we can do is that we can avoid use of this fine solids which are actually creating problem. So no use of non-degradable compositional fine solids like clay and barite will be the best solution for minimizing the formation damage. Then if you're using polymers, we should have an effective check on polymers particle invasion into pay zone. Then we should try to reduce the loss circulation. But we know that whenever the drilling fluid will circulate, may it be in a very smaller amount, but some amount of fluid will definitely get lost to the formation. So the fluid that gets lost to the formation, that is known as filtrate. So whatever filtrate will be going inside the formation, we should try that filtrate should not react chemically with the formation fluid. Otherwise it will lead to formation of insoluble precipitate. So these are the solutions, some solutions that we can make so that we can prevent this or we can control this formation damage. And these solutions we can get in one mud that is known as non-damaging drilling fluid. So non-damaging drilling fluid, it helps in controlling the formation damage. I just would like to show you with the help of this particular diagram. So this is a diagram which is figure which is showing a pay zone section. So this is a pay zone section where a conventional mud has been used, and this is a pay zone section where the mud which is being used is NDDF, that is non-damaging drilling fluid. So here in conventional mud, as I mentioned, we have clay and barite. So these are the fine solids. So whenever the drilling fluid will circulate, it circulates from surface, it goes to the bottom of the hole, again it comes up. So what will happen? The fluid, basically the liquid portion of the drilling fluid, it enters into the formation. And the fine solids which will be present in the drilling fluid, it will also enter. It will enter deep into the reservoir and it will block the passage of oil, and oil will not be allowed to flow from this reservoir to the wellbore. But here we can see that whenever we are using NDDF, we don't have any kind of fine solids. So if there is some loss of fluid also to the formation, there won't be any presence of fine solids to block the passage of oil. So this is NDDF, the scenario that we can get with the NDDF. Then again, whenever there will be loss of drilling fluid to the formation, so what happened? The clay which will be present, so those clays will get swelled up, and because of the swelling of this clay, again it will lead to obstruction of the oil flow from reservoir to the wellbore. But here NDDF is formulated in such a way that when the fluid it gets lost to the formation, so that fluid or the filtrate which will be going or which will be entering into the formation, so that filtrate will be kind of a saline inhibitive filtrate. So that saline inhibitive filtrate, it does not allow this clay to swell and to have interruption to the oil flow. So this is again an advantage of NDDF. Then here in conventional mud as a weighing material, we add barite. But here in NDDF as a weighing material, instead of using barite, we can use calcium carbonate. So calcium carbonate is also a very good weighing material which helps in increasing the density. So whenever there will be like flowing of the drilling fluid, there will be some loss of drilling fluid to the formation. So it leads to formation of a layer of solid. As I mentioned, that whenever the drilling fluid will circulate, the liquid portion it gets entered, leaving behind the solid portion. So that solid portion is known as the filter cake, and the fluid that gets lost to the formation, that is known as the filtrate. So whenever we are using calcium carbonate as your weighing material, so whenever the fluid will get lost to the formation, the filter cake will be formed here. That means it leads to the formation of an external filter cake. But in case of conventional mud, it leads to formation of external. Along with that, it leads to formation of an internal mud cake also, because the solids, the fine solids are entering into the pore spaces also. So removing an external filter cake is very easy than to remove the internal filter cake which will be formed in the pore spaces. So here, because we are using calcium carbonate instead of barite, so it leads to formation of only external filter cake, not the internal filter cake. So whenever it is required, we can remove this external filter cake which has been formed. And again, another point is that in conventional mud, we are using some dispersing agents. So since these dispersing agents are again fine solids, so it leads to problem of plugging the pore spaces and blocking the oil passage. But here in NDDF, we don't use any kind of dispersing agents. So we get this kind of scenario. That means almost no formation damage if you're using NDDF, that is non-damaging drilling fluid. But we may have a lot many disadvantages, and we may have page on damage if you're using a kind of a conventional mud. So this is the advantage of using NDDF over your conventional water-based mud. So these are the different types of mud that I have listed, that is pneumatic drilling mud, oil-based mud, water-based mud, synthetic-based mud, and non-damaging drilling mud. So these are the different types of drilling muds which are generally used in oil industries. Now, basically, if we are talking about drilling fluids technology, its main thing is that to formulate and to develop and to design a kind of a drilling fluid which is capable of achieving the functions, or which is capable of enhancing the properties to the desired level, so that we can have an efficient drilling operation. And there's one more thing, like if we are designing a drilling fluid, if we're formulating a drilling fluid, our first aim is to have an efficient drilling operation. And in that efficient drilling operation, there's one more thing we need to consider, because whenever the drilling fluid will circulate, because of the circulation of the drilling fluid, it leads to various drilling fluid problems. So various drilling fluid problems has been faced by the drilling engineers. So we should formulate our drilling fluid in such a way that it should also be able to prevent those drilling fluid challenges. Then only we can have an efficient drilling operation. I just would like to show you some of the drilling fluid challenges which are being faced by the oil industry people. So first is a stuck pipe. So stuck pipe is one of the most expensive drilling fluid challenges which is being faced by the oil industry. And again, the stuck pipe may lead to various other problems like loss circulation, then well control problems. Now, what is a stuck pipe? So what happened, the stuck pipe situation is basically, encountered if we are having low pressure zone. So suppose this is our drill string which is being running through the hole, and we have a low pressurized zone over here. And here, say suppose the hydrostatic head that we have managed is high. So we have a certain overbalance, and that overbalance will give a push to the drill string so that it will move towards the wall of the bore hole. And if we have a this is the black is showing the filter cake, and if the thickness of the filter cake is very high, so what will happen, the drill string, it will get pushed towards the wall of the bore hole, and it may get stuck in this filter cake which has been formed here. So this situation is known as the stuck pipe situation, and this stuck pipe is known as the differential stuck pipe. This is because of the differential pressure. The drill string has been pushed towards the wall of the borehole, and it gets stuck within the filter cake. So this is one reason, that is a differential sticking we may have. Apart from this, we may have various other mechanisms also which leads to stuck pipe situation, like mechanical mechanisms like pack off, key set. So these are the various reasons which leads to the stuck pipe situations. And if you want to avoid this stuck pipe situation, we can formulate our drilling fluid in such a way that we should be basically able to handle the hydrostatic head depending upon the formation pressure. If we are having a high formation pressure, we definitely should have high hydrostatic head. But suddenly, if a low formation pressure is encountered, we should be able to reduce the density so that we can reduce the hydrostatic pressure to have such a differential pressure which is not giving you, which is not giving a stuck pipe situation. Then there's one more thing that basically what we can do is that we can provide certain lubricating agents which will provide lubrication, which will reduce the torque and drag also. So that will also help in preventing this stuck pipe situation. So this is a very common phenomena which is generally observed and also very expensive phenomena, and this can be prevented if we can formulate or if we can design our drilling fluid in a better way. The next is loss circulation. So loss circulation, that means loss of drilling fluid to the formation. So we may have loss circulation, either natural loss circulation or induced loss circulation. So natural loss circulation means whenever the drilling fluid is being circulated and it is passing through the wall of the borehole. If we have some unconsolidated formation in a certain depth, or if we have certain natural fractures, then that fluid, that drilling fluid will have the tendency that will be a natural tendency that it will simply enters instead of going up, it will simply enters into the formation. So if it is entering into the formation, that means it is getting lost to the formation. So this is natural loss circulation. Then we have induced loss circulation, where maybe because of high differential pressure, as we have discussed here. So maybe because of high differential pressure, or maybe we may have high equivalent circulating density. What happens? It may create some fractures. So that is known as the induced fractures. So because of the creation of those induced fractures, the fluid may get lost to the formation. So this is induced loss circulation, which is not because of the presence of some natural formation, but fractures has been induced artificially, or because of some of the conditions which prevails in the borehole, it makes the mud to get lost to the formation. So this is a loss circulation. That is one of our drilling fluid challenge. Again, if you want to prevent this loss circulation, we can manage our drilling fluid in such a way that we being able to prevent this particular drilling fluid challenge also. Like we can add certain loss circulating materials, one of a component that I have shown you earlier, or some fluid loss reducers. If we add, it will prevent the loss of drilling fluid into the formation, because it will plug those pore spaces, or it will plug the fractures which has been created. So since the pore spaces or the fractures will be plugged, so it will prevent the loss of drilling fluid to the formation. Next is a shale instability. So whenever we are drilling a certain borehole, then there is every chance that at various depth we may encounter shale formations. And shales, basically, if we are drilling through water-based drilling fluid, then shale have the tendency to absorb water. So ultimately it leads to a problem that is known as shale instability. So basically that particular problem is not observed on the very day one of drilling. Generally on the very day one, if we are drilling through water-based drilling fluid, so water will get absorbed by the shale. But the problem is not visible on the very day one. But if you go for a prolonged drilling, then what will happen? The shale will swell more, and that swelled shale will start falling apart. And on day 4, we can see more of the shale portion to it's falling apart, and it may get accumulated to the bottom of the hole, and it may lead to stuck pipe situation. So that means the pipe will get stuck with the shale particles which has been accumulated at the bottom of the hole. So for a prevention, what we can do is that instead of using water-based mud, we can switch over to the use of some oil-based mud or synthetic based mud. But again, using a oil-based or synthetic-based mud may be, may not be cost efficient. So if you want to use water-based mud, then what we can do is that to that water-based mud we can add certain inhibitive particles, and those inhibitive particles will prevent the swelling of shale, and ultimately the swelled shale won't be falling apart to have these kinds of stuck pipe situation. So this is shale instability, one of a drilling fluid challenge, and that can be prevented if we can have a proper formulation of the drilling fluid itself. Then we have insufficient hole cleaning. Like drilling fluid, its one function is to clean the bottom of the hole. But or you can say if we have insufficient hole cleaning, it may again leads to various other problems, like decrease in the drilling rate, loss circulation, wellbore instability, erratic trends in ECD, that is equivalent circulating density. One of a very common problem that we can have is that since the cutting particles are being accumulated at the bottom of the hole, it is not allowed to it is not taken out to the surface. So the drill bit is cutting those cutting particles only. So that means it is grinding and re-grinding the cutting particles only. So the drill bit, it will get worn out. And as I've mentioned, that cutting particles also play a very important role. We take out those cutting particles and we analyze for the evaluation of the properties of the formation. So that part also cannot be done if the cutting particle gets damaged because of the grinding and re-grinding with the help of drill bit. The next is barite sag. So barite sag is a type of a problem which arises if we are using barite as a weighing material. So what happens if drilling fluid is being circulated, then we don't have this problem. But suddenly, because of some reason, say suppose tripping in operation is going on, tripping out operation is going on. So at that particular time, the drilling fluid circulation will get stopped. So whenever the drilling fluid circulation will get stopped, then this barite will have the tendency to move out of the liquid phase and it will get accumulate to the bottom of the borehole. So upper part will be a light mud and the lower part will be a heavy mud with excessive accumulation of the barite. And we know that if we have excessive accumulation of the barite mud, it may again lead to certain other problems like stuck pipe situations. Then drilling through soil formations and rubble zones also, it may lead to certain drilling fluid challenges. Like soil formations are basically plastic formations. So if you are drilling through soil formations, it may leads to certain problems like bit balling. And rubble zones, they are generally present below the soil formations, and rubble zones, they basically comprises of your reactive shale formations. And if reactive shale formations, we know like what kind of problem we may have. Shale instability, then wellbore erosion may take place. So these are the various drilling fluid challenges. Again, those challenges, it depends upon what is the characteristics of the formation. Depending upon the type of the formation also, we may have various drilling fluid challenges. And depending upon how we are formulating a drilling fluid, we may encounter various challenges. So in order to prevent those drilling fluid challenges, basically we should try to formulate our drilling fluid, design our drilling fluid in such a way that it is being able to enhance the properties so that it can be able to carry out the functions which are required so that we can have an efficient drilling operation. So this is about the drilling fluids technology in short. So basically, if we are talking about the drilling fluid technology, so that means it is the like way how we are formulating, how we are designing our drilling fluid. So I just would like to tell you the next half of this presentation, that is its environmental concerns. Since we know that if we want hydrocarbon to get produced, so it is required to do drilling. And if we are doing drilling operations, so that means drilling fluid is an important component, without which drilling operation is not possible. So we know that drilling fluid is a very important component, so its design and formulation should be done very much properly so that it should not have, first of all, it should be able to achieve an optimum performance drilling operation. Second most important thing, that it should also have less effect to the environment. So now I will be talking about its environmental concerns with the drilling fluid. So we know that it will have environmental concerns if drilling fluid, it comes into contact with the environment. So how this drilling fluid will come into contact with the environment? Basically, there are two ways. First is if we are having loss of drilling mud in the well. As I mentioned, that whenever drilling fluid will be circulated, so there will be loss of drilling fluid to the formation during the drilling operation only. So whenever there will be loss of drilling mud, so that means some amount of mud, the additives or chemicals which are present in the drilling mud, it is getting entered into the formation. So that means it is coming in contact with the environment. And second, when the drilling operation will get over, so definitely the drilling mud which is being used for the drilling operation, it is required to be disposed of to the environment only. So these are the two ways by which drilling mud will come into contact with the environment. And if it is coming into contact with the environment, it has two major concerns. First is short-term lethal response to organisms, so alteration of the ecosystem may also take place. And we know that in drilling fluid, we will be having organic compounds and metals. So accumulation of those organic compounds and metals in the environment may contribute to toxic effects in organisms, or it may also travel up the food chain via bioaccumulation. So generally, it is not only with the drilling technology, but all activities which are related to oil and gas exploration and production, like drilling activity, then production activity, then workover activity, completion activity, all those activities, they actually generate waste. And those waste, they cause harmful effect to the environment. Today, I'm not going to tell about all the waste, but I will be specifically focusing on the drilling waste. So there are basically two types of drilling waste, two primary types of drilling waste. One is the used drilling mud and the one is the drill cuttings. So whenever the drilling fluid will circulate, it will circulate from surface, goes to the bottom of the hole, carry the cutting particles and it come up. So those drilling fluid, it is sent to some mud conditioning equipments where the cutting particles are separated from the drilling fluid, and that drilling fluid is reused for further circulation. So those drilling fluids, some are used for the analysis, but maximum portion of the cutting particles are required to be disposed of. So at that particular point, drill cuttings, they behave as a drilling waste. The next is the used drilling mud. So as I've mentioned that the mud, after being treated for this cutting particles, it is reused again and again for the drilling operation. But once the drilling operation has been completed, so at that particular time, the drilling mud, the used drilling mud, it is required to be disposed of to the environment. And that time it will also behave as a drilling waste. So in general, we have two primary drilling waste which is generated. One is the used drilling mud after the completion of the project, and the drill cuttings which are generated on every cycle of your drilling operation. So again, since these are the drilling waste, how much hazard it is causing to the environment, that will depend upon what type of drilling fluid we have been using. So as I mentioned, we have different types of drilling fluid. So depending upon the different types of drilling fluid, the waste which are generated, they have different effect to the environment. Like if we are talking about the oil-based mud, so in oil-based mud we have hydrocarbons which generally don't get biodegrade readily in nature. So they behave as a severe pollutant material to the environment. Basically, as I mentioned, the aromatic excuse me. So the aromatic hydrocarbons which are present, these are the most toxic to the marine organisms, and they cause destruction to soils and groundwater a lot. So despite of having great advantages of oil-based mud, it is generally restricted. Its use is generally restricted. Then if you talk about the water-based mud, the additives and the chemicals which are used in water-based mud, they are the main concern of environmental issues here. For oil-based mud, it is the continuous stream only, and for water-based mud, it is the additives and chemicals which are basically main concern of environmental issues. So that's why Environmental Pollution Agency, they has considered certain metals as some pollutants like zinc, chromium, lead, mercury, cadmium, nickel, and various phenol compounds. So if we are in a process of formulating a drilling fluid, we should keep in mind that we are avoiding these kinds of metals because those metals are creating pollution to the environment. So I just would like to show you some of the, water pollution aspects. So during drilling, there are much chances of contamination of underground water due to contact of drilling mud with it because of mud invasion. So since I mentioned that whenever drilling fluid will circulate, some of the portion of the drilling fluid, it will, enter into the formation. So that is known as the mud invasion. So since it is entering into the formation, it will come into contact with some underground water. And since fluid is entering, that means the additives and chemicals which are being added in the drilling fluid, it is also entering. And it is creating harm to the underground water. So there is one aspect how we can have water pollution from drilling. Next aspect is mud seepage. So mud seepage from the pits, that is also problematic and is a major concern for water pollution. Like we can see in this figure. So here the arrows are showing the flow of drilling fluid. Like the drilling fluid is flowing from the surface, it is going to the bottom of the hole, it is carry the cutting particles, it is coming up through the annulus to the return line to the mud pit. So this mud pit is open to the environment. So if seepage happens to occur here in the mud pit, so the drilling fluid enters into the underground, then it will almost change the composition of the underground water. It will transfer all the pollutants which are present here, all the additives and chemicals, hazardous chemicals which are present here. It can carry those hazardous chemicals underground to the underground water. So it will almost contaminate the underground water. It will create pollution to the underground water. So this is one aspect, that is the pits which are present in the drill site itself. So if seepage happens to occur in those pits, it may lead to water pollution. Yes. Okay. So next is dry pits. Now, what are these dry pits? Basically what happened, the mud pits which are present over here. Okay. And suppose after the drilling operation, everything has been completed, all the equipments, drilling rigs and everything has been moved off, then what will happen, the pit will remain in that place only because it is just an earthen pit, okay, where the drilling or you can say the drilling fluid has been kept over. So what happened, if suppose this pit has not been managed properly, or the drilling fluids which are present over here, it is not managed properly. So over time, what happens, it may get dries off. So the water portion, it may get evaporated and it will convert into a dry pit. So here we won't be having any water, but we will be having the chemicals, the hazardous chemicals in the concentrated form. So as a result, so this will be now become as a dry pit, which is not having any water, but it will have hazardous chemicals in the concentrated form. So if rainfall happens to occur, then what will happen? Those hazardous chemicals, there is every chance of having seepage of those hazardous chemicals to underground, and then it may contaminate the underground water. It may also contaminate the roots of plants and trees, and if we have certain fruits or vegetables are there, and if human or animals they consume those vegetables and fruits, that will also be unhealthy for their life. So dry pits, they are definitely, they cause pollution to underground water, and they can have indirect damage to animal and humans. Like you can see in this picture, this is a reserve pit or mud pit where the drilling fluid is being kept after its use in the drilling operation. All the rigs has been moved up, but this has not been managed properly. So over time, it will get dries off. So all the water, almost all of the portion of the water has been, evaporated. But the hazardous chemical, it has been it has left behind here in the concentrated form. So if rainfall occurs, if seepage is there, it will definitely transfer those hazardous chemicals to underground, leading to underground water contamination. And if heavy rainfall took place and if water accumulates in those disposal sites, then it will behave as a pond, definitely. And that water, everyone will think that that water can be consumed, but consumption of that water will be inappropriate and it will not be safe for the drinking of animals and humans. So reserve pits, which are generally present in the drilling site, they definitely contaminate soil, groundwater, and surface water with different metals and hydrocarbons which are present. Like you can see here, this is just a pit. Basically, in order to avoid this problem, like as I mentioned, that drilling fluid is kept in the reserve pit. We may have migration, we may have seepage. So in order to avoid that seepage and migration, it is generally covered with some liners. Okay, so this black color is liners, which are basically covered cover which is present in the reserve pit to prevent these problems. But again, there is every chance that those liners may get torn out. If again they get torn out, there's every chance of having seepage or migration. And if migration happens, then it may affect the nearby ecosystems and may have hazardous effect to the environment. So several studies have been made by various authors like Veal et al., then Nelson, Rees, who has identified that reserve pits which are present, they may lead to seepage or they may lead to migration of hazardous chemicals to the nearby system, and they may cause contamination to the groundwater, contamination to the nearby environment. So as a result, it is very much important, since we know that drilling operation is like very much important. We know that drilling waste will definitely be generated. So in order to have safe environment, we generally should have a proper management of the drilling waste which are being generated. Now the system which is generally adopted for the management of drilling waste, that is known as the open system of drilling waste management, which is generally adopted by various industries. So what is being done, the drilling fluid which is being used in the drilling process, so in that drilling process, the waste which are generated is cutting particles and the mud waste. So those cuttings and mud particles, they undergo certain initial treatment, and after the initial treatment they are sent to the environment. But just having only initial treatment and then dispose of to the environment is not a safe management technique. So basically, if you are managing a drilling waste, it should have certain approaches. The approaches are like the amount of waste, it has to be minimized as much as possible, and reusing and recycling should be made mandatory, and only those materials which are safe and similar to the local environment should only be disposed of. And based on these three approaches, a kind of a system has been developed that is known as a closed system of drilling waste management. So in this system, the drilling fluid which is being used in the drilling process, definitely it will generate the cuttings and the waste drilling waste liquid portion or drilling fluid. So it should be sent to some treatment process. Cleaning should be done, some treatment like thermal, chemical, biological treatment should be done. Then separation is done. Then after separated, the cutting particles which are generated, those cutting particles can be reused for various other general uses, and the fluid portion or different other mud components, that can be reused for the formulation of drilling mud. Then only the materials which are safe, that can only be disposed of to the environment. And again, from the environment, we can further use other components, like we can use water, we can use bentonite, which is a kind of a clay mineral which is available in the environment only, which is there in the environment only. So from the environment which we have disposed of, that can again be used for the formulation of drilling mud, that can be reused for various other drilling process. So this is a closed system of drilling waste management. which is much more efficient than that of the open system of drilling waste management. So what should be the hierarchy for the waste management, and generally which is being followed by various industries. So same hierarchy should be followed by this drilling industry also, that the most desirable option that we should go is the reduce. That means we should try to minimize the amount of waste which is being produced. Then we should try to use the material again and again. That means we should try to use more than once. Then we should use the materials which are being generated so that we can make certain new products that can be, we can further use for various other applications. Then we should also try to recover certain energy and metals from the waste which are being generated. So this, all these steps will, make you left with a very smaller amount of material that can finally be disposed of to the environment. So this is a waste management hierarchy which is generally followed, and it should be followed so that we can have our safe operation and we can have a safe environment also. I would like to highlight some of the techniques which are generally used in oil industry for the management of drilling waste which are being generated. So first is solids control equipment. Then we have disposal methods for offshore operations. Then we have disposal methods for onshore operations. Then we have thermal methods, which are basically used to do the treatment of the cutting particles. And we have chemical methods, which are basically used to do the treatment of the water, which is being generated. So I'll just tell you in brief about these techniques. So first is a solids control technique. So the solid control equipment, it is generally present in all rigs. If we have a drilling rig, we have this solid control equipments along with the drilling rig. So this is the first waste management practice which is being followed by any drilling operation. So whenever the drilling fluid is circulated from the subsurface, it is sent, when it comes up, it is sent to some mud conditioning equipment. So we have mud conditioning equipments like shale shakers, we have degassers, descenders, and desilters. So shale shakers, they are basically used to separate the large cutting particles from the return drilling fluid. And then descenders and desilters, they are used to separate the fine solids which are present in the drilling fluid. And if the drilling fluid, it has certain entrained gas from the subsurface, it has got some entrained gas. So if you want to remove that entrained gas, we can remove with the help of degassers. So that means the return mud which has come up, we have removed the large particles, we have removed the fine solids, we have also removed the gas particles. So that return mud, it has been treated, and that return mud is again reused for further drilling operation. So in general, the solids control equipment, it reduces the amount of drilling waste which is required to be disposed of. So this is the first treatment practice which is being followed by any drilling industry. So in any drill site, you will be, if you are seeing, if you can see a drilling rig, will be having some solid control equipments also for the first preliminary treatment of the drilling fluid. Then these are the disposal methods for offshore operations. So the different methods which are being adopted, these are offshore discharge, then cuttings re-injection, then transporting to onshore. Basically, they go with the offshore discharge, cuttings re-injection. If these two are not liable to do this, then we go with the transportation to the onshore facilities. So offshore discharge is what? That means it is very simple. Just we are, whatever drilling waste is generated, it is directly discharged to the ocean. And this is economical also. And sometimes it is operationally, safe disposal method also. It is known as an economical method because it does not require any, additional equipment to do that. Whatever is present conventionally on the rig, so that only serves the purpose of direct disposing it to the ocean. But again, it will depend upon what type of mud we are using. If it is water-based mud, then those drilling waste, they generally go for a very little treatment. or without any treatment, it is directly disposed of to the ocean. If it is oil-based mud, we know that oil-based mud, they generally have some harmful effect. So they are actually not allowed to dispose of to ocean. But if it is disposed, for that, certain treatments are done. After that treatment, only it is disposed of to the ocean. So this is for the fluid, that means the drilling fluid that we generally use. And for the cutting particles, if the cutting particles are coming from the water, it is directly, cutting particles are dried and then it is directly discharged to the ocean floor. But if it is oil-based mud, same phenomena is done. It is dried and then it is, put into the ocean floor only. But these cutting particles, which are coming from the oil-based mud, those cutting particles, whenever it gets accumulates over the ocean floor, then the accumulation of those cutting particles may affect the benthic biota, but that benthic biota will recover on its own over time. But how much time it will take, that will depend upon the thickness of the accumulation. If thickness is more, it will take more time. If thickness is less, it will definitely take less time for its recovery. Then one more disadvantage, that whenever we are putting these cutting particles to the ocean floor, it may form some kind of piles over the ocean floor. And basically, piles are formed over the legs of the offshore platforms. So presence of pile only is creating, it will only create problem to the marine environment. And specifically, whenever we'll be having facility decommissioning, that means whenever the operation will be completed and it is required to move our platform. So movement of the platform will disturb the pile which has been formed, and disturbance of pile will have a very hazardous effect to the ocean or to the marine environment. So these are certain disadvantages that we have with the offshore discharge directly. So another method has been employed, that is the cuttings reinjection. So that means instead of directly disposing of to the ocean floor, ocean bed, so what it is done, the cutting particles are grinded into small particles and then they are mixed with some water or some other liquid so that we can make a slurry, and that slurry is then injected at a high pressure to a certain underground formation. So a certain candidate formation is selected, and to that underground for candidate formation, those cutting particles, that means they have converted into slurry and then it is injected directly into that underground formation. Now, there are basically two common ways by which slurries can be injected. One is through the annulus. That means directly, through the annulus, we can, send those cutting particles or send those slurry to the target formation. Or we can send it or inject this cutting slurry through some dedicated disposal well. Basically, injecting through annulus is a cost-effective operation, but the people who are working in offshore, they don't want their well to get damaged. So instead of injecting through annulus, they prefer to injecting through some dedicated disposal well. And about the candidate formation that I have mentioned, underground formation that we will be choosing, so it will also depend upon certain criteria. That means the formation, it should definitely have certain porosity and permeability, then only it will be selected. Then second thing, it should not be related with some underground aquifers. And third thing, it should not pose or it should not have some commercial amount of oil or gas. So the formation which is achieving these criteria can be selected as a candidate underground formation to where these cutting particles can be re-injected. So this is cuttings re-injection, which is a very common practice which is being followed by various industries. Then if we cannot go for the offshore discharge, or if we cannot do the cuttings re-injection, so then finally the one option which is left for the offshore people is that we can transport it to onshore. So basically this is applicable for the oil-based mud, as we know that oil-based mud, directly disposing it to the ocean floor or disposing the cutting particles to the ocean floor is creating problems. So instead of opting for those two methods, they opt for transporting those oil-based mud, the discharge of the oil, or you can say the waste of the oil-based mud to onshore with the help of some ships. Because in onshore we have different methods which can be applied for its safe management and safe treatment process. So these are the various disposal methods for onshore, operations, like on-site burial, then waste pits, landfills. Then we may have bioremediation, like land farming, land spreading, composting, and vermiculture. So on-site burial is what? After the drilling has been over, the drilling waste which is being generated. So that drilling waste has been buried in some. You can see in this picture, the drilling waste has been buried in some natural or man-made excavated pits, and then it is covered with soil. So that means it has been, the drilling waste has been buried inside the earth. So the drilling waste, it has been buried inside the earth. But here again, it will depend upon the type of the drilling waste, because if it contains hydrocarbons or it contains some salts, that means those hydrocarbons and salts again may have harmful effect to the environment. So we cannot bury, because burial, it takes place in anaerobic conditions, so there won't be any kind of further degradation. So this is a one point that we need to keep in mind while going for the on-site burial. Next is landfill. So landfill is almost, we can, similar to that of the burial, but it is not buried. It is like kept and stored in some natural or man-made excavated pits. So here the drilling waste which has been generated, it is put into some excavated areas, and we don't do any kind of treatment, just it is put in store for a particular period of time till that drilling fluid is being sent to some agencies for further treatment or further disposal methods. So this is one kind of a disposal method. It is not a treatment method, where the drilling waste is kept and stored for a certain period of time till it is sent for further treatment. So different oil industries, they have their own private landfills which are generally used for keeping those drilling waste in store for a certain period of time. Then these are the reserve pits or waste pits which are generally available in the drill site itself. As you can see here, this is some kind of earthen pit. Then they are covered with some liners. So the liners are basically some high density polyethylene. The material is high density polyethylene. And to this, after the liners has been put over it, then we can transfer the drilling waste directly to this pits. Okay, so these liners, we need to handle it very carefully, and we need to keep monitoring that there is no torning out of your liners. Otherwise, it may lead to seepage, or it may also lead to migration, creating harm to the environment. Next is the bioremediation process. So this bioremediation is what? That is a biological treatment of the drilling waste which has been generated. So there are various ways by which we can do the bioremediation process, like land farming or land spreading. Then we may have composting. Then we may also go with the vermiculture. So land farming or land spreading is what? That means we take those drilling waste and it is spreaded over some land. And the soil's natural microorganisms, they are allowed to do the degradation of the drilling waste which is present over here. And we also add some water and nutrients so that we can stimulate the biodegradation process. So this is land spreading. Then we have composting. Composting is also similar to that of land spreading only, but here some piles are generated, and what is done here, basically the drilling waste is being added with some bulking agents so that it can increase the porosity and aeration potential. So temperature will increase and volatilization will be there, and it will speed up, it will stimulate the biodegradation process more. So basically it is used in those areas where we have frozen ground. So this is an added advantage with this composting method over the land spreading. Otherwise the process is almost same. Then we have vermiculture. So vermiculture, here we use earthworms. So earthworms are basically used to do the degradation of cutting particles into some organic fertilizers. So they degrade those cutting particles and make some organic fertilizers, and organic fertilizers are then can be used for various other purposes. So this is like treatment of the drilling waste biologically with the natural microorganisms which are present. Then we go with the thermal method. So thermal method is basically used to do the treatment of the cutting particles. So there are basically two ways. One is thermal desorption and the one is incineration. So thermal desorption, this is basically, we can call it as an indirect heating process, and incineration is direct heating process. So in thermal desorption, cutting particles are placed in some treatment unit and they are heated up. Indirect heating is done. So the liquids which are attached with the cutting particles, they get volatilized, recondensed. They are separated into two phases, that is water and oil. So the resulting waste streams that we will have is water, oil and solids, that means the cutting particles, and those cutting particles will be free of hydrocarbons, but since they will contain salts and heavy metals, so we cannot use this directly for various other purposes, but we can use this for road construction, and we can dispose of it by using certain land spreading or landfill methods. Then incineration is a direct heating. So here we do direct heating of cutting particles, and the cutting particles are converted into some solid inert residues. And this is basically done in some air pollution control devices to prevent further emission of the particulate matters. And once the inert residues which are formed, so those are stabilized, and then those residual materials are directly disposed of to the environment. So this is basically, we are we can also say that thermal method is a type of a primary method where first the cutting particles, they are separate out from the water and oil, then cutting particles are treated separately, oil is done separately, and water treatment is done separately by chemical method. So chemical treatment is done to do the treatment of the waste water which is being generated. So various methods of processes can be used. These are the very basic processes, like chemical precipitation, neutralization, adsorption by various absorbing agents, then disinfection by chlorine, ozone, ultraviolet light, and ion exchange, which is basically used to soften the water by displacing the polyvalent ions by sodium ions. So this is a chemical method which is being followed for the treatment of the water which is being generated, so that after treatment it can be reused for various other purposes. So these are the various methods which are actually followed by oil industries, where we can first convert that drilling waste into three phases, and three phases can be treated separately, or we can directly go for the biological treatment. So the remark that we generally get from the environmental analysis of your drilling fluid, we came to know that basically the hydrocarbons which are present in oil-based mud and the chemicals and additives which are present in water-based mud, these are the main contaminant materials. So as is said, like prevention is always better than cure. So if we take early prevention of this particular thing, it will help in have a more environment free operation. So basically, if we do the prevention at the very early step, so early step, that means if we can have proper selection of the additives and chemicals for proper formulation of the drilling fluid and proper selection of the drilling fluid, it will help in enhancement of your drilling operation, as well as it will also reduce the cost of treatment methods as well as pollution associated problems. So basically the main thing that we should know, that if we are since drilling operation is very much required and that can be done with the help of drilling fluid, so we should try to design and formulate our drilling fluid in such a way that it is being able to have the enhancement in the properties to have an efficient drilling operation, plus it should have less effect to the environment. So I just so what can be the steps for a safer environment? Okay, so steps that we can have, we can go with the utilization of some bioproducts, we can go with the utilization of some waste materials, and also we can incorporate nanoparticles, specifically green nanoparticles. So if we can use these materials, it leads to the formation of an environment-friendly drilling fluid. So this environment-friendly drilling fluid, it will achieve both the things, like it will help in the enhancement of the properties leading to an efficient drilling operation, plus it will have a safe environment operation also. So I just would like to show you some of the research that has been done in my lab, keeping this environment point of view. So this is one paper which is being published in Energy and Climate Change. So here the work which is being done is the formulation of rice husk. So rice husk is a waste material, and its use is being seen in the non-damaging drilling fluid and its effect in the shale formations. As we have seen that shale is a kind of a formation where we which is a very common formation which is encountered in every depth, and it is basically kind of a problem creating formation. So if we can develop a kind of a mud which is less reactive to the shale, so that will be more advantageous. So these are the various equipments which are being used. This is Hamilton Beach mixture to formulate the mud. This is the mud balance to determine the density. This is a marsh funnel viscometer to determine the effective viscosity. This is fan VG viscometer to study the rheological properties of the drilling fluid. This is methylene test, blue test kit. This is filter press to determine the filtration property. Then this is the water analyzer, which is used to determine the pH. This is basically used to determine the amount of bentonite which is present. This is not used in non-damaging drilling fluid, but it is used if you are doing experimental analysis with bentonite based, because if you're using a bentonite based mud, it is very much important to find out what is the amount of bentonite we are using, because it has a certain maximum limit. So we have done the experimental analysis with starting with the formulation of a non-damaging drilling fluid, and for the formulation we have used various materials like CMC, carboxymethyl cellulose, calcium carbonate, potassium chloride, sodium hydroxide, partially hydrolyzed polyacrylamide. So first we have chosen the optimum concentration of CMC by looking into its cost and technical efficiency. Then we have used that optimum concentration in the second phase, 2000 ml of distilled water. Then the same experiment we have done with this calcium carbonate and all other additives to find its optimum concentration. And we have found out that for CMC calcium carbonate, the optimum concentration was found to be around 0.25. Then for percentage, then for KCl and sodium hydroxide, it is around 0.35, and for PHP, it is 0.3. So once we have got the optimum concentration, we have formulated the drilling fluid, non-damaging drilling fluid, and to that we have analyzed the concentration of rice husk, various concentration, its effect to the properties. One more factor we have considered for determination of the optimum concentration, that is the yield point to plastic viscosity ratio. So generally an ideal mud should have a ratio between 0.75 to 1. So from this we have come to know that this particular concentration is giving near to ideal value, that is 1, and this is 0.3. So this is again one factor which helps to determine the optimum concentration. After we have prepared the non-damaging drilling fluid, we have checked the effect of the different concentration of rice husk. So we have found out that as the concentration of rice husk increased, the effective viscosity is increased, then the filtrate loss, its value decreases, and we have done the analysis with different other additives, and we have found out that rice husk, which is a kind of a waste material, it behaves as a very good filtrate loss reducing agent. Then we have analyzed the NDDF that we have prepared with rice husk for the shale formation, and to analyze the shale formation, basically it's a shale stability test. We have taken the shale sample from Shamphai district of Mizoram. We grind it to small particles, dried it, and we have put those shale samples into the 2 tarsons. So here up to 7 ml, we have put the shale samples, and then we have put the NDDF, that means the mud we have prepared up to 14 ml. And the second mud, this is mud 1, which is NDDF, and to the second mud we have added bentonite based mud, and we have prepared the bentonite based mud just by adding 1% to the NDDF that we have prepared. So we have put the mud in the 2 tarsons up to 14 ml, and we have started monitoring the level of fluid volume. So if the fluid volume level is decreasing, that means the shale is absorbing water. So we have monitored every 2 hours, and we have keep monitoring up to 24 hours. And what we have observed that for mud 1, the fluid volume, it reduces from 14 to 13.4. So that is for NDDF. And this, the bentonite mud, the fluid volume, it reduces from 14 to 13. So just by adding only 1% of bentonite, it is showing that the volume of fluid, it reduces more. That means more amount of water is getting absorbed by the shale formation. Now, after that, we have taken out those shale sample. We have put it into the filter paper, and then we have dried it. So we have collected some, determined certain important, values like what's the wet weight, what's the dry weight after immersion, and what's the initial dry weight. Putting those values in these equations, we have found out what is the swelling percentage and what is the spalling percentage. So for NDDF, we have found out the swelling percentage is 46.883, whereas spalling is 3.821. But for bentonite mud, we have seen a higher swelling percentage, that is 68.540, and the spalling percentage is also more, that is 7.319. So from this analysis, we came to know that NDDF is far more better than that of your bentonite-based mud in enhancing the properties of the drilling fluid, as well as it also helps in preventing one of a very common problem, which is generally observed in oil in drilling industry. So that is the shale instability. So NDDF is much more stable in case of shale than that of bentonite-based mud. So this is for a waste material we have carried out. Similarly, we have carried out for some bioproducts also. So we have done experimental analysis with plant extracts. So here we have chosen 2 leaves. One is mango leaves and the one is the neem leaves. Their extract has been prepared, and from those extract, mud has been prepared and the rheological properties were analyzed. And it has been observed that with increase in the concentration of both the mango leaf extract and neem leaf extract, the value of plastic viscosity increases. And we have also looked into the yield point. Yield point value also increases with increase in the concentration. But yes, with increase in the temperature, both the plastic viscosity as well as yield point value, it decreases. We don't see any much difference to the filtration properties, but the mud cake thickness, it reduces, like with increase in the concentration of both mango leaf and neem leaf extract. We have also tried with some environment friendly additive, and we did the comparison with the commercial additive which is being used. The one is the CMC, carboxymethyl cellulose, and what we have chosen is the polyethylene glycol, which is much more environment friendly. So we have done the analysis separately, and we have found out that introducing PEG to the drilling mud, and as we go with the increasing the concentration of PEG, the plastic viscosity value increases, filtrate loss, it reduces, mud cake thickness also reduces. And we have given another attempt like combining both CMC and PEG to make it more cost efficient. So with the combination, we have kept the CMC concentration constant is 1 gram, and we have increased the concentration of PEG. So we have observed that with increase in the concentration of PEG along with 1 gram of CMC, it is showing more increase in the plastic viscosity, decrease in or enhancement in both rheological as well as filtration properties. We have also done the shear stability test, and we have observed that in comparison to that of CMC, PEG is more efficient, and if you do the combination of CMC with PEG, it is much more efficient. Here I have shown one paper. If anyone is interested, they can go through it. Like here, various bioproducts has been reviewed and has been mentioned, which are basically used for the enhancement of various properties of the drilling fluid. Then we have also thought of incorporating nanotechnology. The muds which are generally used are water-based or oil-based in drilling industry. They basically comprises of chemical additives. No doubt they enhance the properties, but they also cause damage to the formation. So instead of using those muds, we can also shift to the nanomuds. So why nanomuds? Because the nanoparticles, they have high surface area to volume ratio. Since they have high surface area, a smaller amount of nanoparticle will help in enhancement of the properties to a very higher level. And we have certain added advantages, like it conducts heat efficiently. They are also thermally stable at high temperature and high pressure conditions, because this is very much important, because some of the additives, they behave adversely, like they behave differently in the surface, and they generally show complete opposite effect in the subsurface. Like some additives, they are showing very good increase in the viscosity in the surface, but if it goes downward, it may show decrease in the viscosity. So there are certain additives which shows these kinds of phenomena, but nanoparticles, they are very much thermally stable at high pressure, high temperature conditions. So we can use this for higher temperature or deeper depth wells also. So we have also conducted some experimental analysis. We have done experimental analysis with iron oxide nanoparticles. We have checked its efficiency in the enhancement of the properties. Like we have synthesized the iron nanoparticle using ferric chloride as a precursor and reducer as sodium borohydrate. So we have used different molarities, and to each molarities we have used different reducers, different concentration of reducers, and we have prepared various nanoparticles, and we have observed that as the molarity of the ferric chloride increases, the value of plastic viscosity increases, and also as the molarity of your reducer, that is sodium hydrate, increases, the value of plastic viscosity, it also increases. So as the molarity of reducer increases, the value of plastic viscosity increases, and as the molarity of ferric chloride, that is a precursor, is increasing, like from 0.1, 0.2, 0.3 to 0.5, we can see the enhancement or increase in the value of plastic viscosity. So that is, here we can see 3 to 4, here we have 4 to 6, here we have 6 to 8, here we can have much more higher value of plastic viscosity. Same we have done for the filtrate loss also. We can see that there's a good reduction in the filtrate loss value with increasing the molarity of the ferric chloride, as well as the funnel viscosity, effective viscosity, it also increases with increase in the concentration of nanoparticle in our nano fluid. So this is just a picture of some of the nano suspensions, that is from 0.1 to 0.4 molarities. As the molarity increases, the color is also changing. Then here we have also looked into the mud cake thickness. So for 5%, we can have a greater thickness is there, and if the concentration of nanoparticle increases, the mud cake thickness, it also reduces. So these are the two papers just have shown to show that nano is not only applied in drilling, but it is also used in various different fields of oil and gas industry. And as I mentioned, that if you are talking about nanoparticles, using a green nanoparticle is much more efficient. So if anyone is interested, they can go through this paper, which is showing a review on synthesis and application of green nanoparticles. So basically, if you want to synthesize green nanoparticles, we can use various elements like, from various compounds, we can prepare the green nanoparticles like bacteria, then we may have, yeast, then algae, fungi, bacteria. Then also from the plants, we can prepare the green nanoparticles. So from basically in our lab, we have till now done the synthesis of green nanoparticles using this plant extracts. So this plants, they are taken, their extract has been prepared, and from those extracts we can prepare the green nanoparticles. So in the similar way, we can use other compounds also for the preparation of other things, also for the preparation of green nanoparticle. And basically the particles which are nanoparticles which are generated biologically, they are pharmacologically more active than the other which are synthesized physicochemically. So this is an added advantage we can have. So basically we can incorporate these bioproducts, we can incorporate these waste materials and also green nanoparticles for the formulation of drilling fluid. So this will not only help in enhancement of the properties, as we have already seen in some of the experimental analysis that properties do change, they do enhance it. So properties will also enhance, and along with that they will be more environment friendly also if they are directly disposed of to the environment. So this is about the drilling fluid technology and how we can have a safer environment approach if we are talking about the formulation of a drilling fluid. So this is all from my side. Thank you so much everyone for patience listening. Thank you so much.
Thank you for your nice presentation. So, participants, any queries or questions? Or you can write us in not get
Prasun sir, your voice is not coming.
Voice is not coming?
Yeah. Please take the mic closer.
Is it all right?
Yes.
Now it is all right? Voice is okay?
Yes, I can
Yeah, it's
hear
perfect.
you.
Participants, any queries or any questions? You may write on our chat box also. I think no question is there. So thank you once again, Dorcas, for your nice presentation. And on behalf of everybody present in this program, I want to thank Dr. Borsha ma'am for her informative and interesting presentation on the topic drilling fluid technology. This is an important topic which is as far as the petroleum technology is concerned. So we appreciate your for sharing your knowledge and expertise on drilling fluid. So once again, from all of us, thank you. Thank you.
Thank you so much for having me in this presentation. Thank you so much, everyone.
Prasun sir, your voice is not coming clearly. Take the mic closer.
Is it all right? Is it all right?
Yeah. Keep it closer, please.
So today this is our second, though it is the second session, this is our last session, and there will be no further session today. So we'll wind up here for today, and there is no afternoon session for this today, as the session was shifted to Tuesday, and already it is completed. So on behalf of the Department of Petroleum Technology, Dibrugarh University, I would like to thank all the participants for joining and attending the sessions of day 4 of the Faculty Development Program. My sincere thanks goes to the research person for sharing their knowledge and expertise through their talks and presentations. Please join us again tomorrow at 10 a.m. and that will be the last day or 5th day of our Faculty Development Program. Thank you once again, and we will share later on the feedback form link. Okay. Thank you everybody.